Good morning, everyone. Thank you so much for attending the second day of the third summer school in control of complex robotic system. Today we had the opportunity to know more about the motion control of parallel kinematic manipulator. Thank you so much, Ahmed, for bringing us this opportunity to meet about the work you developed for this kind of robot and the challenges of control. So please introduce Ahmed. Thank you.
Thank you very much, and good morning, everybody, and thanks a lot for coming again. It's a pleasure to see you again and to tell you more things about control of complex robotic systems. So today we have two lectures. So the first one, it will be about the control of parallel kinematic manipulators, and you will see through the presentation itself why this kind of robots they are interesting. Why the control problem is not so easy, it's very complex control problem. What are the challenges associated to the control of these robots? And I will show you some of the control solutions that we developed in our lab. And the most important part, I will show you real-time experiments to see, the performance of the controllers that we develop in real time on those robots. So just to sum up, as yesterday I present you the plan of the lectures that we will have, and we start yesterday with the first lecture that gives you an overview about robotics today. Then the second lecture, it was about the control of under-actuated robotic systems, and today we will have two lectures. And the first one, it will be this one, and we will talk about the control of parallel kinematic manipulators. And let's get started. To start, I will show you two short videos just to see a real application where these robots are used, for which application. And the first application, as you see here, it's a parallel robot here, as you can see, and this is a big cabin, and this is a drive simulator. And if you want to learn about or do training for driving a car, so you can use this simulator. So inside you have the environment of the car, it's like a real environment of the car. And here outside, around, you can see a screen with the video of simulating the motion of the car. And the motion here is guaranteed by this parallel robot that try to generate the same dynamics of the car. And this parallel structure, it's a parallel robot that is moving this big cabin. And the idea, as I told you here, it's to reproduce the same dynamics of a real car. So the first question that you may ask here, why we use those robots for this specific application? Because those robots, they are reputed by their high capacity of payload. You can put a huge payload here, and then you can control the parallel robot to move this payload in 6 degrees of freedom. So the workspace is small, however, the number of degrees of freedom is 6. So you can have X, Y, Z, and also roll pitch U. And this is very nice because in the nature, if you want to reproduce the dynamics of the car, it's moving and it's moving to the right, to the left, when you take like a curve and so on. So it's possible to reproduce this. And the good thing here, you can reproduce different environment. Like here you look, it's driving during the night. And this is very good for the training of the drivers. So this is first example that shows you a parallel kinematic manipulator used for a driving simulator. And here they mounted this parallel platform on a moving linear platform to combine more motions, to have a higher speed and accelerations and so on. And here it's just the interface of this simulator. You can choose where you are driving, if you are in the city, outside the city, during the night, during the day, and so on and so on. Nice. I will show you another video or so, almost the same application. And here it's another simulator. It's a flight simulator. And as you can see, this reproduces the dynamics of an airplane, a small airplane. And as you can see, the pilot is sitting here. And this is held by this parallel robot. And the control actions here of the pilot are linked to the control of this hexapod. We call them hexapods, these parallel robots. And the idea is to reproduce the dynamics of the airplane, as you can see here. So this is just to introduce the context where these kind of robots are used. And now let's go further in this lecture. So this is the outline of the lecture. So I will start with the general context. And then I will try to talk about the control problem formulation, because it is the most important thing for us, how we can control these kind of robots and what are the main challenges in terms of control. Then I will talk about the real-time experimental platforms. We have different kind of robots that are used for validation of the proposed control schemes. I will show you some of them. Then I will talk about some of the proposed control solutions. Here I put just some examples. I will not have time to develop all the controllers. I will give you the link where you can download the papers, but I will show you just some examples. Then real-time implementation, and then the last part, I will show you real-time experiments to see how those controllers have been implemented and what are the performances. And as you can see, different kind of robots are used for this validation. So let's get started with the general context of these parakinematic manipulators. And let's start from the basics. Let's go back to the basics. And let's, like robotic manipulators that I introduced in the first lecture, and as I told you, they are based on open kinematic chains, and these robots, we call them serial robots, because as you can see from the structure, it's a sequence of articulation and body, articulation, body, and so on, going from the base here, which is fixed, to the end effector. And here you have one example of those robots. It's a robotic manipulator. And we call this a serial robot. Now, let's introduce the parallel robots, parakinematic manipulators. So the structure is different from this one, since actually it's based on closed kinematic chains. Here it's an open kinematic chain, because you start from here, you arrive here, you don't close the chain. However, here, you start from this point, you go here, and you go back, so it's a closed kinematic chain. So this is the main structural difference between serial manipulators and parallel manipulators. First thing to keep in mind. And then, as you can see, you have here 1, 2, 3 kinematic chains. And the number of kinematic chains, it can be 2, it can be 3, it can be 4, it can be 6, it can be 8. There is no problem with the number. And all those kinematic chains, they are in parallel. And here you have one example. As you can see the parallel kinematic chains here, and the end effector is here, and the base is here. So this is the first concept to understand, to start, how parallel robots are constructed. What is the difference between the kinematics in the case of parallel robots compared to the kinematics of serial robots? Now, let's compare the properties, because every manipulator has properties. And if you compare properties between like serial and parallel robots, what are the differences? Here in the table you can see the property here, and then you can see how this property is for the serial manipulators and how it is for parallel manipulators. So if we take, like, for instance, any example, if you take, for instance, the preferred property, the best property for those robots. So for the case of serial manipulators, it's the dexterity, because dexterity is how the degree of motion that you can get in the end effector. So here it's a high dexterity, it's very good. This is the best performance for serial robots. Now for parallel robots, the best or the preferred property is stiffness. Why stiffness? Because actually if you put kinematic chains in parallel, you improve the stiffness. This is very known. I mean, you take one kinematic chain alone like that, even if it is stiff, if you put more, it will be more stiff. So you have a better stiffness here. Like for instance, the preferred application. For the case of serial robots, you have big motion. Sometimes you can have a big workspace, so you can do a big motion in this case. However, for parallel robots, it's the precise positioning. It means that the end effector, you can position the end effector with precision in the workspace. I will show you by the end of the presentation some experiments with some robots where the precision was very, very, very nice. The order of micrometer, like the maximum tracking error of our controller on those robots, it was like around 20 micrometer of precision of tracking of trajectories. So they are very well known by this precise positioning. Now, if we talk about dynamic, the model in general, so we have, like for instance, the kinematics and forward and inverse kinematics. You know what is kinematics? So forward kinematics, it's a model, a mathematical model that gives you the transform from joint space to operational space. So this transformation is based on the forward kinematics. And for the case of serial robots, it's very easy. It's straightforward and unique. You can have a model, you can compute it very easily using like trigonometric equations, sinus and cosinus and so on. And you can obtain this model that express the position orientation of the effector in terms of the joints of the robot. So this is for the case of serial robots, which is straightforward and unique. However, for parallel robots, it's much more complicated. It's much more complicated if you suppose that you know the joints of the robot and you want to obtain the values in the operational space. And for the inverse kinematics, it's the inverse. It means that to invert a forward kinematic model for serial robots, it's very complex because you have highly nonlinear equations to be inverted. However, for the case of parallel robots, it's straightforward and unique. It's very easy to compute an inverse kinematic model for parallel robots. So on, you have a lot of, like for singularity, we have static singularities for serial robots and kinematic singularities for parallel robots, and so on. After this, let me show you a short video. And in this short video, it's introduced what is a parallel robot.
And actuators.
And it's
interface between the mobile platform and an actuator is
this is the moving platform.
The actuator is powered with an electrical motor. The interface between
this is the
and
hardware.
an actuator is done with ball joint.
This is joints.
The actuator consists of a fixed part, the body, and a mobile part.
This is one leg.
The shaft is doing a translation in the body. The mobile platform is linked to the base by 6 identical high-precision actuators. The mobile platform can move along the x-axis.
The degrees of freedom:
the
1,
y-axis laterally,
2,
the z-axis vertically,
3,
it can rotate around the x-axis,
4,
the y-axis, pitch,
5,
the z-axis, yaw.
and 6.
These moves
6
are
degrees
not
of freedom.
directly on actuator's range. Here only one actuator is controlled. This structure makes it possible to realize the fine positioning of the mobile platform following the 6 degrees of freedom. The high-precision actuators are electric powered by a motion controller inside a control enclosure that commands the position. This control enclosure is linked via Ethernet to a computer on which the user can manage moves and position of the
This is the interface of the control.
By defining his own user reference axis in the software,
This
the
is
user
what
is
you can
able
do
to
with
set up for the hexapod a new center of rotation and
this.
position the mobile platform in order to this reference axis.
With respect to this reference.
The hexapod is able to support heavy payloads. The stiffness of the various components constituting the hexapod guarantees high stability and positioning quality in vertical and even in horizontal orientation. The hexapod can be used for static positioning application over time, but also for dynamic applications such as swell
And you
simulation,
can
for
see
instance.
this application in real life. So those robots are used for this kind of applications, and they are coming from this company. It's called Symmetry. We have a strong cooperation with this company. We did even, actually we have 2 industrial PhDs with this company. I explained further, so they had some problems in terms of control, and they come up with our lab to discuss about those problems, and they proposed us to resolve those problems. And we worked jointly together. We took one PhD student, he spent half time in the lab, half time in the company, and we worked on these real problems of the company, and we resolved those problems. I will show you some of the videos by the end that shows the controllers that we developed to resolve the problems of robustness of this kind of robots. Anyway, now in general, parallel robots, they are used for several applications. A lot of applications. One of those applications are here, as you can see. I have shown you some of them at the beginning of the lecture. So as you can see, this is a flight simulator, this is a car simulator, and this is a boat simulator. So you can use them for motion simulators in general. Why? Because actually, several reasons. So the first reason is that they can carry a heavy payload. So you can put a cabin. Imagine that here it's not A320, but A380, the biggest airplane. Okay? You can imagine a very huge cabin here, but you can put it on a parallel robot, so it's able to manage to carry this payload and to move it in real time. So this is the first reason. The second reason is the high dynamics. It means that you can increase the speed and the acceleration, and you can generate very high dynamic motions. This is why we use this kind of robots for motion simulators. And the third reason is the precision. If you want to generate a motion with a precision, you can get this high precision using this kind of robots. And for all those examples here, it's what we call them hexapods or steward platforms. They are used for those motion simulators. Another application, and also it's thanks to the high precision of positioning of those robots, they are used in medicine. For several medical applications, we can use parallel robots. They can be used like for rehabilitation. You can do an exoskeleton based on a structure or parallel structure. And they can be used also for other kind of surgery because of the high stiffness and the high precision. Also, they are used in nuclear applications like for synchrotrons. Sometimes you need a very high precision of orientation of the head that is used in nuclear applications, and parallel robots, they are very well appropriate for this kind of application. Then also the same, for telescopes, sometimes you want to get a specific orientation of your telescope, and you want to get it with a high precision because you have to look to some stars, take some pictures or something like that. In this case, you can use parallel robots, and they are very well appropriate for this application due to the stiffness and the high precision. They are used also for another application, as you can see here from this picture. This is food packaging. Food packaging, it's you have food here. Here in this case, it's chocolates. You take the chocolate coming on a belt, you put it in a box, and you repeat this operation as fast as possible. And here we don't use the same structure. As you can see, between this one and this one, it's not the same. This is a steward platform, but this one, it's a Delta-like parallel robot. It's a lightweight parallel robot, and here the basic idea, you know why we designed this robot like that. I give you a question. Imagine that you are in the traffic in the city, you are moving, you are in your car, on your left there is a bus, on your right there is a motorcycle, and you are at the red light. When it goes from red to green, which one starts moving? The bus, the car, or the motorcycle? Which one? The bus, the motorcycle, for sure. Why? Because the motorcycle is smaller. It has low mass and low inertia. So it means if you want to go fast, you have to reduce the mass and the inertia to be able to go fast. The bus, it's heavy. The inertia is big, the mass is big. So it takes time to start. Then it comes the car, then it comes the motorcycle. The motorcycle is the highest in terms of speed. And here, if you see the structure, look to these parts are moving here. They are constructed by carbon fiber material, so they are very lightweight, this moving part. So the idea in the Delta robots is to reduce the mass of and the inertia of the moving platform, moving parts, such that you can go faster. And I will show you one of our robots with which, as I told you last time, we reach a record of maximum acceleration equal to 100 G. 100 G is the gravity, so 10 approximately, so a maximum acceleration of 1000 meters per second square. And this is due to several things, to redundancy in actuation, to the controller, and also due to the structure. We reduce the mass of the moving parts. Then we have another application, it's machining. Also, we are interested in our lab to do machining using parallel robots. You know CNC machines, or CNC devices, they are used for machining. We can use also parallel robots to do machining. Then we have another application, as you can see here, it's for agriculture, where you can see a mobile robot on which we mounted here a parallel robot, a Delta parallel robot, to do some tasks in agriculture. And the last application here, as you can see, is the problem of waste sorting. And I will show you, I will go further in this because we have been interested in this application. So from this slide, you see the potential or the most important applications where parallel robots are used. Now let's talk about control, because we are interested in developing controllers for this kind of robots, and let's try to formulate the control problem. And I will try to do this through some applications, through concrete applications. I will not start with mathematics, I will start with physics, with something real. We want to do this application, how we can resolve the control problem for this application. And the first application, it's here. And it concerns what? Food packaging. So in food packaging, I will show you a short video, and also I will explain on this video. What is the idea? This is the Quattro robot, and it's used for food packaging, as I told you, and the idea is to do what we call pick and place tasks. So you pick an object from here, you put it in the box, and you repeat this operation as fast as possible. So from the video itself, from the application, it seems that the task itself is very easy because it's not very complex, the motion is easy, you have just to go from one point to another and you repeat this operation. So it seems to be easy, however it's complex. Why it's complex? Because actually here what we want to do is to increase at maximum the speed and the acceleration. Why? Because we want to increase the productivity in industry. So we have to increase the speed and the acceleration. However, if you increase the speed and the acceleration, you may generate some problems. What are the problems? Let me explain first. If we analyze the motion that you have here, this is what we call pick and place tasks. It means that you have object here, the end effector is here, you take the object, you put it here, and you repeat the operation. So let's analyze what we call a pick and place cycle. It starts from here, the end effector is here, you have an object here, and you want to take this object here to put it here and go back. So the pick and place cycle starts from here, you take the end effector until the object, you take the object, you grasp the object, you go to the place position, and you go back to the initial position. So this is one pick and place cycle. And if you decompose the pick and place cycle, it's the different motions that we have shown here. And pay attention to something. Look here, what we call pick position and the place position. These are what we call the stop points. They are stop points. It means what? It means that you have to go there, stop to take the object, you take the object, and then you move the object to the place position, you stop to place the product, and you go back. It means that if you want to increase the number of picks per minute, you want to increase the productivity, you have to reduce the cycle time. And to reduce the cycle time, you have to increase the speed and the acceleration. However, if you increase the speed and the acceleration, pay attention, you will have two stop points. It means that you have two stop points. You have to stop to take the object, accelerate at maximum, and then you have to stop to put the object, and then you go back. And the problem is, when you stop here, you accelerated before, and you stop here, you may generate mechanical vibrations. When you stop, you will have mechanical vibrations. And instead of reducing the cycle time, you may increase the cycle time. Why? Because here, when you reach the object, you oscillate. If the oscillation is not smaller than a certain threshold, you cannot go back because you are oscillating. So you have to pay attention to this problem of oscillation, okay? And we can reduce this problem of oscillation. It can be through the control, it can be through the optimization of trajectories that's used for the pick and place and so on. So this is the first application we are interested in, and we want to resolve this problem by designing controllers for these high-speed motion tasks, okay? So this is the first task. Now let's move to the second application. And in the second application, we are interested in machining. So machining, it's also a task that may be very complex. Why very complex? Because you have the machining tool here, which is in interaction with the piece, and you have to move. You have two kinds of motions. You have the same as the previous case, pick and place. When you, like here, you are doing pick and place. You move from one point to another. And once you enter in contact with the surface of the piece, you have to follow a predefined trajectory. Like here, for instance, you are following predefined trajectory, and the quality of the piece that you are machining, it depends on the precision of the tracking. I mean, if you do a good tracking, you have a good piece. If you do a bad tracking, you will have a bad piece. And here it's challenging also due to the interaction. You have the interaction between the tool and the piece, and you have to manage this interaction. So this is the second application we are interested in, using parallel robots. Now let's move to the third application. And for the third application, we are interested in something else, which is also interesting, and this is what we call waste sorting. It means that you have the waste coming on a belt, and the idea is to do sorting. It means you have to put the plastic in a box, the wood in a box, the paper in a box, and so on. You have to do the waste, the sorting of this waste. Here, as you can see, the application that are using parallel robots also, and here they are applying the same concept as the previous video. They are using the concept of pick and place. They pick the object, put it in the box, and they repeat this motion depending on the objects that you have here, and they put the boxes on the right and the left of the belt, and they repeat this operation. In our case, instead of this, we propose something else. Why we propose something else? We propose something that we call pick and throw. I will explain why and how we propose this solution, and the idea is also to go faster, to do this waste sorting in a faster way. Now, before I talk about control, let me introduce the experimental platforms, because as I told you yesterday, the objective of our research activities is to develop control solutions and to validate them on real-time experiments on some experiment platforms. Here you have some examples of robots that we are using in our case. Let me introduce them first. So the first one here, it's called R4, and here, as you can see, it has 1, 2, 3, 4 molders. It has what we call here the arm. This is the forearm, and this is the moving platform. The moving platform, as you can see here, is the end effector, and it has 3 degrees of freedom, X, Y, and Z only. However, here, what we have as control inputs or molders or actuators, we have 4. Remember what I explained yesterday. In the case of ender-actuated robotic systems, you have less molders than degrees of freedom. Here is the inverse. We have more molders than degrees of freedom. So this is the case that we call over-actuation or redundancy in the actuation. And also in terms of control, it has a big problem to be resolved. This is the experimental platform, and here, as you can see, the whole platform with the mechanical part, with the computer used to control the robot, and here the structure that uses the hardware. It uses MATLAB Simulink with explicit target as toolbox that you have used, and you implement your controller on this computer, but you have another computer. You have 2 computers. So the first one here, you have MATLAB Simulink. You develop your controller, and then you compile your controller to generate the C code. The C code will be uploaded on this computer. The second computer is something specific. It's an industrial computer with a higher computation capacity. So you upload your code here, and it's executed in real time, and it is connected to the robot. So it sends the control actions, and it gets back the measurement from the sensors. In terms of measurement for this robot, we measure just the joint positions. So Q1, Q2, Q3, Q4 only. And then from this we can compute the speeds, we can design the controller, and so on. So, and here, as I told you, the most big problem in terms of control, it's the actuation rhythm. Nice. So the second example here, it's another robot called Veloz, and Veloz, it has exactly the same structure here, the upper part. The only difference is here, because here it's what we call a rigid moving platform. There is no articulation. In the case of Veloz, here the moving platform is articulated, and it's articulated in this way. Why we add this articulation in the moving platform? In the case of pick and place tasks, I have shown you some videos. The idea, as I told you, you have objects here. You take an object, you put it here, and you repeat the operation with. Sometimes, like for food packaging, imagine that the box is oriented like that, and the object is oriented like that, and you want to put it here, or the inverse, like that, like that. This is the box, this is the object, I want to put it inside, like that, not like that, like that. So I have to take the object, to move like that, then like that, and they have to rotate before I put it inside the box, otherwise it will not enter. So this is why we need a rotation, and to create this rotation, so we transform the rigid platform to an articulated platform, and it's articulated like that. We have 2 parts, the upper part, the down part, and 2 arms are linked to the upper part, and the 2 other arms to the lower part. And here in the middle we have a screw, and if you move the upper part with respect to the lower part, you create this rotation. I will show you this in the videos. And this is the real-time experimental platform, the same as the previous one. We use explicit target. this is the robot, this is the industrial computer, this is the development computer, and we implemented the controller on this one. The next one is something else which is different, and here we are interested in, like, for machining. If you want to do machining using a laser, you have a laser cutter. A laser cutter, you can fix the head here, and the idea is to follow a predefined trajectory to cut the material through or following a predefined trajectory, representing the form of the piece that you want to cut. So you fix it here. The structure is completely different because it uses the same molders here, as you can see, as the previous two examples. They are rotating molders. However, the structure is different. Here you have the arm, the forearm, and the moving platform is here. So it's different. It's different because here, look here, the structure, or here, but here it's in the plane, the structure. And if you move the four molders, here this moving platform can move along X, Y, and a rotation along Z axis. It has also 3 degrees of freedom, it has 4 molders, and we have the problem of actuation redundancy. The same problem. And this is the real experimental platform that we have in our lab. And as I told you, the laser cutting head should be fixed on the moving platform or the end effector of the robot, which is here in the middle. Next one, it's also a robot designed for machining. And here for machining, it's the structure is completely different from the previous cases. You know why? Because actually for all the previous cases we using are rotating molders. Now we replace them by linear molders. We have 1, 2, 3, 4, 5, 6. And they can move along these lines. Okay? Here you have 2 molders, here 2 molders, here 2 molders. Why? Why we replace the rotating molders by linear molders? You know, one of the objectives of this robot is to do the machining of big pieces. Like for aeronautics, they need to design big pieces. So a small robot, because the previous one here, or for instance here, the work, look, this environment that you see in blue here, this is the workspace of the robot. Only the end effector cannot get outside from this workspace, so it's very small. So to avoid this problem of limitation of the workspace, we replace the rotating molders by linear molders to increase the workspace, because we want to do machining of bigger spaces. So this is the robot, this is the kinematics, we see the 6 molders, and the application is here for machining. This is, I will show you a video, machining of this piece like with a pyramid shape, and this is the moving platform. This is the moving platform, or the tool is fixed here, and the parallel platform, and the linear actuators are here. This one, this one, this one, and you have 3 here also. And the last one, it's also for machining, but we go back to the previous structure, and the previous structure, it's used like 4 motors and 4 arms and arms like that. And here it's called Spider 4, and one of the specificities of this robot, you know, you are able to measure the end effector in the workspace, because all the previous cases we can just measure the joint positions in the motors, but here you can measure the position of the end effector in the workspace. As you can see here, it has arms, 4 arms, and the moving platform is here. Let me ask you one question regarding the machining task. It means like regarding this one and this one. For CNC machines, how many degrees of freedom we need to do machining? How many? 2 or 3 or 4 or 5 or 6 or 7, how many? If you look to most of CNC machining, so all of them, they have a certain number of degrees of freedom. How much is this number? Do you know? 3? No. 3, it's not enough. 3 is not enough. How many? 6. 6 is 2, it's 2. It's a lot. So it's between 3 and 6. 4, no. 4 is not enough also. 5. 5 is a good number. But now you have to explain me why 5. Why not 4? Why 5? You are doing machining. When you do machining, what we use? We use a tool, and the tool is rotating. So if you take any object in the space, it has 6 degrees of freedom. So we can do machining using 6 degrees of freedom. However, we have to remove the degree of freedom of rotation of the tool. 6 minus 1, you obtain 5. Okay? So here, for this case, we need 5 degrees of freedom to do machining. Look here. The moving platform, it has 4 degrees of freedom. So X, Y, Z, and 1 rotation. So we need 1 more degree of freedom. How we can get it? Look here, this is a turntable. We have a motor here, and the piece will be fixed here, and we can rotate the piece. So the 5 degrees of freedom, it's here outside. And here, the parallel platform, it has 4 degrees of freedom. It means that this one, it has X, Y, Z, and the rotation, and then the second rotation, it will be here. And the rotation of the tool here, this degree of freedom, we remove it. So we have 5 degrees of freedom. Now for the case of Spider 4, how we can get 5 degrees of freedom? Because it's exactly the same as the first robot R4, which has 3 degrees of freedom. As I told you, it has, I mean, if you look until the red part here, going from the motors to the red part it has 3 degrees of freedom only, X, Y, and Z. So we need to add 2 rotations. How we did this? What we did, look here, this is a serial robot fixed on the parallel platform. So it's parallel platform like that, and you fix 2 degrees of freedom, okay, a serial platform. This one and this one are the 2 motors. So you create this rotation here and this rotation here. So 2 plus 3, you obtain 5 degrees of freedom for machine. Now, let's now talk about the proposed control solutions that we designed to resolve this kind of problems. And for remember the 3 applications, so pick and place, the case of machining, and the case of waste sorting. So I will show you the proposed control solutions. Then I will try to show you experiments of validation of those controllers. This is some examples. So we designed a lot of controllers to control this kind of robots. And as you can see from this slide, look in red, the term that is repeated many times here. Adaptive, 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 everywhere. Why adaptive? Because for all the applications that I have shown you before, we need something to be robust, a controller to be robust enough. And adaptive control, it's a robust controller, and it can manage the situation. Let me explain something. Why we need this robustness? I give you a simple example for the pick and place. For the pick and place, as I told you, you have just to take objects from one place, put them here, and you repeat the operation. The problem is the object that you are carrying by the robot, you suppose that you don't know it. I don't know the mass, I don't know the inertia, I don't know any information about this, because I want to design a controller that works for this object and this one also. And the weight of this one and this one is not the same. And the same, the inertia is not the same. So in this case, we need a robust controller. And in the robust controller, or the adaptive controller, we can estimate the mass of the object in real time. This is what we did. We designed a controller. When we take the object, we estimate the mass and the inertia, and we can compensate in the controller. So this is why adaptive. If you take the other applications, the waste sorting the same. We suppose I take a box, I want to put it for plastic, for instance. When you take the bottle you don't know if it is empty or it's full. You understand? I take a bottle like that and I want to put it in a box. I don't know if I don't know the mass, I don't know the inertia, I don't know if it is full or half full or it's empty. You understand? And this is an uncertainty. And this justifies the development of robust or adaptive controllers. Okay? So this is that just to justify the choice of adaptive controllers, and here the different platforms on which we validated our controllers. So I will try to introduce some of those controllers. I will not have time to detail all the controllers. If you are interested, I will show you the papers. You can download all our papers online, and you can read carefully about the different controllers. I choose just to show you maybe 2 or 3 controllers that we tested. And the first one, it's a controller that we call dual space feed-forward control. So what is the basic development of this controller, and what was the origin? The origin of this controller, you know, it was on this robot, R4, that I presented before here, and they explained the story of development of this controller. So, and this robot was designed to reach this maximum acceleration of 100 G. We were working on a research project where the objective, the name of the objective, we know it's named Objective 100 G. This is the name of the project. And we want to reach this record of maximum of acceleration of 100 G, and we designed this robot. However, when we start designing controllers and implementing controllers, we had an issue. We started implementing a controller, model-based control called computed torque control that you know. You have the dynamics, and you have the controller which is based on the dynamics. And we tried to implement it, However, one of the big problems that we have, you know, is the computing time. Because for this computed torque, the computing time was bigger than 0.1 milliseconds. What represents 0.1 milliseconds? The sample time of the robot. So here the hardware, we choose it such that we have to get the measurement, compute the tracking error, compute the desired error, the desired trajectory, the tracking error, the control input, and send to the actuators in a time, all this in a time less than or equal 0.1 milliseconds. So with the computed torque, it was not possible. So then we have to design simpler controllers. And one of the simpler controllers, it was the PID. So we started with the PID, because the PID, it's like you have 3 gains multiplied by the error, the integral of the error, derivative of the error, compute the sum, and then you send this to your robot. So it's easy. But the performance of the PID, it's not so good because it has a limited performance. So we started first with the PID, and we designed the PID in the operational space. It means that here you look, you have the desired trajectory of the moving platform in the operational space. We use the inverse kinematics to go the joint space. We get the measurement here from the sensors, from the encoders on the motors. We get this measurement, we compute the tracking error. We obtain the tracking error in the joint space. And then we use the Jacobian matrix, H here, to move the error in the joint space to the error in the operational space. And then the PID in the operational space, we obtain here forces in operational space. We have to go back to the joint space because we send here torques to the motors. We use the transpose of the Jacobian matrix, we obtain tau, we send it to the robot, and we close the loop. So this was the first controller that we tested. Why this? Because of the simplicity, because the constraint of the real time was satisfied here. However, the performance, it was not enough, and in this case, what we proposed to improve this. And to improve this, we proposed something else, to keep the controller and to add this. How we call this? So if you have a feedback, you get the feedback here and you design the controller, this is a feedback controller. And if you do this, how we call it? The feed forward. It's the inverse of feedback. It means it's based on the desired trajectories, not on the measurement. This is a feed forward, and this is another feed forward. So it's a geospace feed forward because we have 2 feed forwards, one in the joint space and one in the operational space. And as you can see, this one, it's in the joint space, and this is operational space. And then we obtain the control input and send it to the robot. So this is the first controller we designed, and then we try to improve again this controller. We found that the problem is here, how we can tune the gains of the feed forward. And to avoid tuning of the gains, and we want to propose something that works autonomously or automatically tuned, so we proposed an adaptive version. So in this case, we tune autonomously the gains of the feed forward here, and this is why we call this controller geospace feed forward adaptive control. So the previous one, it was not adaptive here, it's just the PID with feed forward, and this one, it's an adaptive feed forward in geospace controller. So this is the second control approach. And now, the third control approach, it's a desired compensation adaptive loop. What is desired compensation adaptive loop? If you know adaptive control, the idea is to have here proportional derivative gains. This is the proportional, this is derivative like a PD controller. This is the adaptive control term, and this is what we call the regressor. And this is the parameters to be estimated or adapted in real time. And this is a robustness term. I don't know if you are all familiar with adaptive control or no. I can explain the basic, but I need the white box or a black box I don't have. But, and also the time. Anyway, so adaptive control, it's based on the estimation of the parameters in real time. And the parameters that are here, we are estimating them. And this is what we call the regressor. And the regressor mainly for classical adaptive control, it's based on Q, Q dot, and Q dot dot. However, here in this case, we replace Q dot, Q dot dot by QD, QD dot, and QD dot dot. It means the desired position, desired velocity, desired acceleration. Why? Because if you use the measurements, position, speed, acceleration. It means Q and Q dot and Q double dot. If you look to the robots, what we can measure? Only Q. We cannot measure Q dot, we cannot measure Q double dot. In all the robots that I showed you, all of them, we can measure just positions. It means that you need to compute the speed by derivation, and you have to derive it again to obtain the acceleration. And when you compute the derivative, as we have seen yesterday, you amplify the noise. And to avoid this problem, this controller is called desired compensation adaptive law because they replace Q by QD, Q dot by QD dot, and Q double dot by Q double dot D, desired. And this will reduce the effect of the noise. Okay, so this is the idea of this desired compensation adaptive law. This is the robustness term. This is the proportional derivative term. This is the adaptive one. And the definition of the tracking errors, the combination, like in sliding mode, the speed and the position. And this is the adaptive law that is used in this case to estimate the parameters phi here. What are the advantages and drawbacks of this decal, the desired compensation adaptive law? The advantages is the desired trajectories are in the regressive matrix. It means that you reduce the effect of the noise. This is an advantage. A reduced noise effect. This is the consequence. Reduced computing time because the regressive matrix can be computed offline because you know from the beginning your reference trajectories and you can compute offline those terms. So it's an advantage. And no inversion of the mass matrix. You have not to compute the inverse of the inertia matrix that takes time. So these are the advantages. And then the drawbacks. It has some drawbacks. A feedback loop with constant gains. It means that here Kp and Kv or Kp and Kd, they are constant. Okay? So, and this is a drawback. It's better to design gains that vary with the time varying gains. Okay? Limited performance for high accelerations. Remember that you want to go very, very high acceleration towards very high accelerations, and the performance may be limited in this case. Sensitive to external disturbances also, if you have something that modifies the environment or the robot itself or the interaction or the objects. So this may generate this sensitivity to external disturbances, and limited tuning capabilities because the gains here are fixed. So what we proposed as a solution to improve this decal controller is to replace the gains, which are constant, by nonlinear time varying gains. Gains that may vary with the time. So in this case, we replace these two gains by gains that can be computed online in an automatic way. Okay, they are time varying. They are nonlinear gains. I explain here. This is the proportional. This is the derivative. And this idea may work for any controller that uses proportional derivative gains. I mean, if you have a PD controller and you want to make it nonlinear, you can use these two gains. Now let me explain why we choose here, like for the proportional gain like that. You will understand here, it's the tracking error because Kp is multiplied by E. And here you have E and here you have Kp. So if the error is small, okay, near zero, we have to increase the gain. If the error is big, it's like here minus or plus, the gain will go to smaller values. And between them, we have exponential variation. Why we did this? Because if the error is big and you have fixed gain, and you take big gain, big multiplied by big, you obtain very big. So it means you can have oscillations. If the error here is small, you can increase the gain because the error is small. So in all the cases, here, big error, we have a small gain, and small error, we have big gain, and there is a compensation. And this is why we propose this. And then you can ask me why we put a threshold here, Kp. Because if we continue the exponential, it goes to infinity here. If the error goes to zero, so if we continue this exponential, it goes to plus infinity. And we have to avoid this. This is why we limited the error maximum here, and this is a saturation or a threshold. So this is the Kp, the same idea for Kd, also for small and big errors, and we obtain this. And these two gains are used here, and the obtained controller is called nonlinear decal or nonlinear feedback controller. And here for the mathematical expression to obtain gains time varying like that, this is for Kp and this is for Kb. Now the question is, okay, we replace fixed gains by time varying gains, but the question is, what about the tuning? because actually the tuning, if you are a PD, the previous case, constant gains, you have two gains to tune, KP, KP and KV, two gains. Now, with the new proposed structure here, how many gains you have to tune? You will have 6 gains to tune. I explain why. Look here, for this first gain KP, you have to tune alpha 1. Alpha 1 is the exponential, okay? And you have to tune delta 1, is this threshold here. And you have to tune KP. So instead of KP, you have KP, alpha, and delta, 3. And the same for KV. So you have 6 gains to be tuned. And this is a problem. So it will become more complex to be tuned. So just to pay attention to this. And this is the advantages. So a rapid transition with the feed-forward damping, robustness towards changes in the parameters. All those are advantages of the proposed controller. So, and this is the block diagram of the proposed controller. KP, KV here, as you can see, they are time varying. This is the model-based adaptive feed-forward. This is the design trees. This is the definition of the errors E and ED. And then we compute the sum here, and then we send it to the robot here, and you get the feedback. Just something which is very important, if you implement this controller on a redundantly actuated robot, it means you have more actuators than degrees of freedom, that I explained before, you have to add this term here, okay? And this term, if you want to know more, have a look to the paper and have a look to the references in the paper. You understand why and how we computed this Jacobian matrix transpose multiplied, pseudo-inverse multiplied by the Jacobian transpose. You obtain this term that reduces the internal effort that may appear due to this redundancy in the actuation. So this is the third controller. And the fourth controller, it's another controller called RISE. And RISE is coming for robust integral of the sign and error. And how this controller it works, this is the name. It's a non-model-based controller. You don't need to know the model. It's like a PID, you understand? You don't need to know the model, because when you write the control input, you don't need to know the parameters, the matrices of the dynamic model. And it features a unique signal function. We will see this signal function. This is the control input. If you analyze the control input, so it's based on, look here. This is a proportional derivative, because here E2 is a combination of the position error and the speed error. And combining both of them, you multiply by gain Ks plus 1, you obtain a PD controller here. I will explain this term later. Let's go to the next one here, the integral of gain alpha sigma plus here beta signum, the sign function of the error E2 here. And this is the control input. Now, the last term that I didn't explain here, you know, if you don't put this term and you design a controller and you have an initial tracking error, you can start with a very big control input. If the gains are big and at t equals 0, there is a tracking error multiplied by big gain Ks, you can have a very big control input. So you may start your robot with abrupt motion, big motion. So to avoid this, you have just to remove the error at t equal to 0 when you start from this one. It means if you look to this equation, at t equals 0, it starts from 0. So this, by doing this, you guarantee whatever your situation is, you start from a control input equal to 0 at t equals 0. Okay, this is the idea. And this control, as you can see, look, it's the integral of the sign function here. It's like the high order sliding mode control. It's not exactly the same, but it's the same nature. Here you have the advantages and drawbacks of the RISE feedback controller. Stability of the system is guaranteed. You can prove the stability analysis. It's high order nonlinearity is taken into account. It can work with large class of general disturbances or so, and it's very reasonable hypothesis that you make when you design the controller. However, it has also some drawbacks. And any controller in the world, it has advantages and drawbacks. And here some of the drawbacks may lead to a high gain or high frequency feedback, the chattering, okay? Stability not guarantees in the case of hard nonlinearities. And also you can have poor performance in the presence of large disturbances and uncertainties. So in this case, what we propose is to augment the RISE controller with a model-based feed-forward control. Because this controller, it does not take any model information, it's non-model based one. So if you have a dynamic model, you can add the information of the model and you obtain a model-based controller combined with the RISE controller. And this is the proposed idea. So this is the RISE controller that we presented before, and we add, look, this is what I presented before in the CAL. It's an adaptive term, the regressor multiplied by the estimated parameters, and you obtain the control law, which is here. And here is the adaptation mechanism and the definition of the different tracking errors. And this is the block diagram. So the block diagram, it shows you the original controller and also the extension that we proposed. So this is the model-based extension feed-forward, and this is the original controller and the whole block diagram. That's it. Now, next, the last controller is L1 adaptive control. Also, I will try to explain quickly due to the time, but let me introduce the basic principle of L1 adaptive control. I don't know, anyone knows here L1 adaptive control? No. Let me explain the origin of development of L1 adaptive control. But with the white, oh, it was much better. Can you bring one?
Yes.
Yeah. Please ask two students, they can help you maybe, or because I need to write to explain. But let's introduce first the concept. Look, if you look to adaptive control in general, they have adaptive controls, non-linear adaptive controllers. They have some drawbacks that are here. First of all, you in the previous case, like for instance here, look here, for instance, you are estimating the parameters here, okay, using this adaptive law and this regressor. One of the problems of adaptive control, how did you choose the initial values of the parameters? I mean, look, you are implementing this. What would be the initial value of the parameters? You don't know the parameters, you are estimating them. How you initialize them? Yeah, so in this case, you need to have what we call a priori knowledge. It means I am estimating this parameter, it should be around 10. I initialize 9 or 8 or 15, you understand? Not far from the real value. This is first thing. And this is not all the time we have this a priori knowledge. This is one issue. Second issue, you know when you do adaptive control, you have to decide about the reference trajectories. If you take very simple reference trajectories, thank you, but we need the table. Huh? Okay, thank you. Waiting for the table. So, you know we estimate the parameters using this adaptation law. How we can guarantee that you will converge? You start with the initial value that you choose based on the priori knowledge, but how you guarantee that you converge? You can move, you can converge if you excite. I want to move. Look, I am here. Look, here I push. Does not move a lot. Look, does not move. But if I push like that, it moves. So this is excitation. This is what we call persistent excitation. So you need appropriate excitation for the parameters to move to converge. And this is linked to the reference trajectories. If you have a simple trajectory, it does not excite enough the parameters, and maybe you will not converge. So you need a reach in frequency trajectories to excite the parameters to be able to converge. And this is the second issue. I'm not talking about L1 adaptive control. Pay attention. This is classical adaptive control. They have these issues. First issue, second issue. And third issue, when you are estimating the parameters, look to this law. You have here K. It's what we call the adaptation gain. The best way is to converge quickly. Real value is here, you are here. If you converge slowly, it does not work because in the meantime, you are not using a good gain and there is error until you converge. So the best way is to converge quickly. And to be able to converge quickly, what you have to do? You have to increase K. To increase K, you can converge quickly. However, if you increase K enough, you may have oscillations. So there is a compromise between stability and convergence of speed. So you may destabilize the system, and due to this increasing of the parameter K. So high gain adaptation gains may destabilize the system. And all these are issues of the classical adaptive control. And the Sure. Thank you. Okay, fine. That's good. Nice. So all these issues, and L1 adaptive control was designed to avoid all of them. How they decided, how it was designed? It was designed based on a decoupling between robustness and adaptation. Why? And how they did this? Using a low-pass filter. If you do a decoupling between robustness and adaptation, the consequence is the following. It means that you can initialize your estimated parameter to 0. I don't know them. I have no priori knowledge. I put everything in 0 and it works. The second consequence, I can increase the gains. There is no problem, no limit. I will not destabilize the system. I will keep the stability. Why? Because you know the controller is based on low pass filter that will filter the action of the controller. Even if you increase the gains, the control action will be filtered and it will be okay. There is no problem of instability. And the last consequence, the parameters excitation, you don't need this. Simple trajectories should work. All these advantages, we get them based on the L1 adaptive controller. If you go back to the story of adaptive control, you know the first adaptive controller developed in the world, it goes back to, you know, when the first adaptive controller developed in the world. Give me a date. Give me just, you can try.
80s?
Huh? 80s? No, before. 60s? No, before.
20?
Huh?
20s?
No, after.
Orange.
After.
50s.
50s. And you know the origin of developing of adaptive control? It was, the problem is time, I can tell you the story. By the 50s, after the Second World War, they were working on the control of airplanes, like military airplanes, okay? To control the airplane, you need the dynamics. At that time, they're using the PID controller. And they use a model. And for the PID, you need a linear model. So you have the non-linear model, you linearize, you obtain the linear model, you design your PID, and then you use it in real time. And you know, the problem is, for the airplane, when you change the speed and you change the height, the dynamics may change. And they design the PID, they put it in the airplane, and when the airplane changes the autopilot, I mean the altitude and the speed, there has been a crash because the PID was not able to keep the performance. And they try to understand from where it's coming, and they notice that it's coming from the PID controller. And at that time, what they propose to do, they propose to do a table, okay, like a table like that. For instance, I will try to put here, for instance, here it's the speed, and here it's the altitude, and I will put all the different values that the airplane can have, like here speed, I don't know, 100, 1000, something like that, and the same here. And for each two values of the altitude and the speed, they have the gains, Kp, Kd, Ki, okay? And the same for each possibility. And then in real time, they switch. I am here, then I move here, they move to the new gains like that, and they have the new gains. Then you move here, take this, take this, take this, and so on. And how we call this adaptive controller? The first adaptive controller in the world, it's called, when we switch between the gains. Exactly. This is the principle of gain scheduling controller, okay? And it was designed around 1950. Now, L1 adaptive control, it's very recent because it was developed, look here the date, 2010, here. So compared to the original adaptive control, it's very, very new. However, it has a lot of advantages, as you can see here, compared to the classical. This is one of the first adaptive controllers, but you have also model reference adaptive control, and you have different kind of controllers, direct and indirect and so on. So the advantages of L1 adaptive controls are here. Now let me introduce how L1 adaptive control is working, how it's obtained. And before that, I have also to explain to you the basic of model reference adaptive control. Who knows model reference adaptive control? The others know? Okay, let me explain the basic principle. It's very easy to explain, but I need to...
You ready? Okay.
No problem, I think. So let's start with the idea of a PID controller. Everyone here knows PID controller. So PID controller, so you have here your system to be controlled, and then here you put your PID, and then you close the loop. Here it's very easy. You have the tracking error, you have the reference here, and you have your controller. And here you have your three gains, so KP, KI, and KT, okay? And you design your control based on the desired performance. It means your closed loop, here you fix the performance I want to get this overshoot, this settling time, and so on and so on. Once you design your controller based on this system, you tune those gains to obtain this performance. However, if something changes here, the performance may be lost. You may lose the performance. You introduce a big uncertainty here, or disturbance, or uncertainty, okay? So this may change the performance, and you will lose the performance. The idea of model reference adaptive control is the following. So first of all, you have to define what we call a reference model. What is a reference model? It's something that you put here. It's a mathematical model. Here, reference model, okay? And this reference model, it will be your reference, your desired dynamics, your desired performance. And this performance that you defined here, you put it inside. It means you choose your model such that you will have exactly this performance that you desire. It's defined by this model. And then your closed loop here, you try to be as close as possible to this all the time. It means what? It means you take the output here, the output of your system, you compute the tracking error between the reference model and your closed loop, okay? And once you obtain this error, you add here adaptation mechanism. Adaptation mechanism that comes here to tune automatically the gains of the PID controller. And you give the input here, and this is what we call model reference adaptive control. So it means what? It means that if something happened here, automatically you will detect this through the error between the reference model that doesn't change and your system that changes. The closed loop changes. So we detect an error here, but it comes into the adaptation mechanism that will tune the three gains such that you will be all the time like the reference model. So you keep the performance whatever the change that you have here in your system. So this is model reference adaptive control. And you know the L1 adaptive control, it goes from the idea of this. In the edge, the basic principle of L1 adaptive control, it's the following. This is the closed loop system of L1 adaptive control. Let's get to this block diagram step by step. First of all, we start from what I explained in the table here. Model reference adaptive control. Look, this is your system. This is the reference model that I put here. We compute the error between them. You have adaptation law. You come here, you adapt your control input, your controller, okay? And you have the closed loop. So to get from the model reference adaptive control to L1 adaptive control, first thing to do is the following. You replace the reference model by a state predictor. Previously we had a reference model, look here. We replace by now a state predictor. And state predictor like an observer. Look, it's the same structure as the original system. This is the first step. Second step, you add a low pass filter. So the control action here, it was not filtered. You have to filter it by a low pass filter. And the last thing, since the estimated parameters here theta and hat, how you can guarantee that they will not go to infinity? They stay bounded. How? You cannot. So to be able to guarantee that the parameters are bounded, you will add the projection operator here. When you do the estimation, you add the projection and you guarantee that the parameters are still bounded. And by these three modifications, you obtain L1 adaptive control. So this is the basic idea. So you can look to the, if you want to study in more detail this controller, I suggest you to look to this book. Okay, you can get this book. I have a copy of this book if you want. And it's explained everything in detail with 12 chapters or more. And you have all the theory behind L1 adaptive control. So I will not have time to say more, but let me go forward now. This is the advantages and drawbacks of the L1 adaptive control, because in our case, at each time we try to improve the controllers. You have seen from decal, we proposed an improvement. Here the same for L1 adaptive control, we try to improve the L1 adaptive control. The main advantages of L1 adaptive control, decoupled estimation and adaptation that explained, specified performance, parameter boundedness that we guarantee through the projection. No dynamic model is required because the model that you use here is not the real model of the system. It's like a desired model, reference model. And it has some drawbacks. The estimated parameters lose their physical meaning because we'll have some parameters to be estimated, but they don't represent physical meaning. Okay. Then all uncertainties are considered with a known structure. This is in the design of the controller itself. Here you have the parameters theta, and you have also sigma, and you have omega. You have three kind of the parameters. This is for the mono input, mono outputs, single input, single output systems. For multiple inputs, multiple outputs, so we will have three parameters, sigma and theta and omega to be estimated. And do not take the advantages of the knowledge of the dynamics. So if you have a good dynamic model, why you don't use it? So we can use a dynamic model. This is why we propose to augment the L1 adaptive control with a model of the system, okay? A feed-forward model. And this is the dynamic model of the robot, and this is the control input, and this is the proposed control law that we propose. So this is the L1 adaptive control, two terms, the feedback one, the adaptive one, but we add a feed-forward term here. The different terms, state feedback, the adaptive one, and the feed-forward, which is based on the dynamics, and as you can see, look here, QD everywhere. QD, QD dot, and QD double dot. So it's a reference model that you used in the feed-forward. And this is the adaptation laws for theta and sigma, and as you can see, the projection to guarantee that the estimated parameters still bound. And this is the block diagram of the proposed controller, the L1 adaptive controller, and the extension by this feed-forward, which is here. And if your robot is redundantly activated, you have to add this term here before you send the control input to the system. And the same advantages and drawbacks of this proposed new controller. And then what we propose now, it's another version which will be an adaptive feed-forward. Okay, so we will make this feed-forward adaptive. So this is the relative error. This is the adaptive term, and we make it adaptive here. We have to estimate the estimated uncertainties. And this is the term which is model-based. The previous one, it was not adaptive. It was like just a feed-forward, as you have seen here. There is no adaptation. We take just dynamic model. We replace QD everywhere, and you obtain this feed-forward term. And now, in our case here, we replace this by an adaptation here, a regressor multiplied by the estimated parameters. This is the adaptive feed-forward term, and this is the block diagram with the adaptive feed-forward here added to the L1 adaptive controller. Now let's finish with the real-time experiments that we obtained. First of all, one of the controllers that we developed, it was a dual-mode adaptive controller. I didn't detail the controller here, but you can find it in this paper. And we did experiments on this parallel robot. For pick and place, as I told you before, for pick and place, you can have the case where you take an object, put it here, and you repeat the operation, okay, something like that. So this you operate in a plane. You need just 2 degrees of freedom. It means that you need this motion and this motion, 2 degrees of freedom. Sometimes you need more, you need 3. Like I need to put the object like that. It means I take the object, this is 1 degree of freedom, 2, and they have to rotate 3 and put it. Sometimes you need 4. So you are here and you want to put it here. So you have 1, you have 2, you have 3, and you have 4, rotation. So for pick and place, you may have 2 or 3 or 4 degrees of freedom needed to manipulate the object, okay? So here on part 2, it was a robot designed for only 2 degrees of freedom, so the motion in the plane. And let me show you the obtained experimental results. So this is motion, pick and place. This is pick, this is place, and you replace the motion. Okay? So we start the motion in the plane, It has two active joints, two passive joints, a rigid platform, and it's moved in the plane. This is the moving platform where we put the end effector. It has 135 grams. Remember that we need to reduce the mass and the inertia. To do this, we have three possibilities: serial structure, parallel structure, or spatial structure. So we choose this case. And this is the two actuated arms in red and the passive arms here in green. And the passive arms are here just to keep the motion in the plane. So I will show you some results. 10 g of maximum acceleration. Cycle time 0.48. 20 g 0.35. 20 g, 30 g 0.28 seconds cycle time. 40 g 0.23 seconds cycle time. And the maximum 50 g 0.21 seconds cycle time. Did you understand what we mean cycle time? It's what I explained before. It means that I take the object, I put it here, I go back, this is one cycle time. So if the cycle time for 50G is 0.21, approximately 0.2, it means in 1 second, how many objects you can pick? How many seconds per second? How many? If you pick one object, 0.2 seconds. In 1 second, I can pick 5. In 1 second, I can pick 5 objects. So you can imagine the speed and acceleration of this picture. Nice. Another example is for 100G. So we started first with two scenarios, pick and place in 3D with 30 and 40G. And between 30 and 40G, you will see the difference. It's not the same. Look here. So here is 30G and here it's 40G. We'll do a 3D pick and place. Look here, 40G. And if you compare with 30G, you can see the difference between them. So also in this paper, you can see the details of this controller. So we start with 30 and then 40. And this is just another scenario to test the robustness of the controller. We add 200 grams of the mass, and we suppose that we don't know this mass, and we test the controller for this mass variation. Then now let's see the case of 100G. For 100G, we didn't do this motion because of the security of the robot. So we do a vertical motion. We increase the amplitude, the speed and acceleration until we reach 100G. And then we reduce to go 0 progressively in a smooth way. Let me show the video, and you will see that the camera was not able to follow the motion of the robot because it was very, very high speed motion. Here we go back to the middle, and we start. Look, and look the noise until we reach 100G, and then we go back to 0. So it was not possible to follow the motion of the moving platform using this camera. It's not a high-speed camera. Anyway, let's go ahead. Another result, you have seen DCAL, the direct compensation adaptive law. We proposed an extended version. We tested this on dual robot here, and we tested these trajectories here, moving. The second scenario, it was adding a payload which is unknown. We add this payload and we try to repeat the same trajectories to test the robustness of the controller. Also the same in the paper, you can find the details. Here some results for the nominal case. You can see the tracking errors. The red one is the original controller and the blue one is the extended control that we proposed. 13% of improvement. The estimated parameters, as you can see, look here, the initial condition and the convergence of the estimated parameters. All of them, they converge. And also the robustness test, 14% of the improvement. The payload, we suppose that we don't know the payload, and look, we have the estimation that converges to the exact value of this payload, which is unknown. Then rise controller with versus the adaptive rise controller that we proposed in the same robot dual V. We tested also the nominal case, and then we tested the robustness test where we add a payload and test the performance of the controller. Let me show some curves. Nominal case, 34% of the improvement of the tracking errors. The estimated parameters, look here, the mass and the inertia of the payload. So we take the object, we suppose that we don't know it. And the adaptive controller is able to estimate it in real time. And now the robustness test case, 53% of the improvement. the estimation of the added payload here, and also the L1 adaptive controller compared to the L1 adaptive controller extended with the feed-forward. The same in the papers, you can find all the details of the proposed controller. I just explained here the general concept, but the mathematical details are in the paper. Here you can see the rotation of the moving platform that I explained before on Velos, using comparing L1 adaptive controller with the extended one with the feed-forward. Okay, then the obtained results here, the tracking error, as you can see, 68% of improvement in terms of tracking performance. As you can see, the blue curve, it has a better tracking performance than the red one, and then the estimated parameters are here. And the video compared, so the L1 adaptive control compared to the L1 adaptive control with an adaptive feed forward, and here it was on arrow. You can see the motion. And here we are not doing machining, it's just demonstration of the motion of the degrees of freedom. Here we have 4 degrees of freedom of this moving platform, and this is the reference trajectories. And then they obtained curves here, as you can see, 79% of improvement in terms of tracking error when you extend the L1 adaptive control to feed forward based on the dynamics. The tracking error, root mean square, 7.4 micrometer. You can see the precision of the tracking. And estimated parameters here. Then the machining task. So with arrow, this is the turntable, as I told you, it can turn, it has 1 degree of freedom. And the moving platform, it has 4 degrees of freedom. And here we are doing the machining. It's a demonstration. We want to do the machine of a pyramid shape, and you will see the final shape at the end of the video of validation of this controller. So this is the final shape that we did in this case. Let's move ahead. We still have a lot of videos to show. Here it's the same machining. Look to the turntable. This is what I'm talking about. You will see that it will turn like that. So we change the orientation of the piece, and then we start the machining. Here with a higher speed of motion. The same idea is to do the machine of pyramid shape piece here. You can see the motion of the linear motors here, the moving platform, the tool is here, and the piece is here. The piece is in black. This is why we cannot see. The table is in black and the piece is in black. This is why we cannot see clearly the piece which is here. Anyway, let's move ahead. Now, a cooperation with La Salle University, as you can see here. This was within PhD of Jonathan Escorcia that I co-advised with Ippolito here, and he worked on the control of this Spider 4 robot, and here he developed an adaptive rise feedback controller, and you will see the results that he obtained here for machining using the Spider 4 parallel robot. So this is the piece that he wants to do machining. He chose the speed of the motion. This is the speed of motion of the tool. And as you can see, you have two cameras. One camera that observes the robot and one camera that will observe the machining task here, or the interaction between the tool and the piece. We move forward the piece is here. It's the white piece, it's white here, the color of the piece. Here we have a free motion, and then we enter in contact with the piece, and we start following the predefined trajectories of machining. The same you can see in this paper that we published together, all the details of the adaptive rise feedback controller. Now you follow the predefined trajectories of the machining. You lose the contact with the piece. You go to the next point, and then you enter in contact, and you follow the predefined trajectories of machining. And we evaluate the controllers for different situations, different speeds of motion also, and to validate the proposed controller. So the next one is what we call pick and through for waste sorting. Here we develop optimal trajectories for pick and through. Let me explain just the basic principle. The first video that I show you, the waste sorting, they use parallel robots, they use pick and place, something like that. So they take the object from here, from the belt, the waste, put it in a box, and put it in a box. They have to go there to release the object. In our case, we say, okay, we want to go faster. I suppose that the box is here. This is the box. I take the object here and I want to put it there. I am not obliged to go there. and also it's outside the workspace of the robot. So I will do something like that. I will throw the object. I pick the object and throw the object. Pick and throw. And to do that, you will gain time, because in the middle of the trajectory you throw and you go back. You take another object, so we'll have more picks per minute. So this is what we did here, and this is the obtained results. We compare our method, pick and throw, with pick and place, and also we found in the literature one pick and throw method. We compared our method with this one, and we show that it's better. For low speed, look, 24, 30, almost the same, just slightly more. But for high speed, we will see that we increase the difference between pick and place and pick and throw. Pick and place 51 and 150 pick per minute for pick and throw. So it's much bigger. And here inside the workspace, we compare the existing pick and place and our pick and throw and our pick and throw, almost the same. And then for higher speed, we will see the bigger difference between the existing pick and throw and ours. 75 and 120 pick per minute. And here we can throw the objects outside the workspace of the robot. This is the existing one, and this is our method, and the same for high speed. We throw the object outside the workspace, 65 and 81. And then we compare both for different situations, low speed, high speed, and the proposed one, existing and proposed, low speed and high speed. That's it for this one. So the time is going very fast. Just maybe 2 or 3 last videos quickly. This is the joint PhD that we did with the company, industrial PhD, and it was on motion simulators or flight simulators. They use this Stewart platform. We want to follow these predefined trajectories, and we developed here an adaptive robust sliding mode control. Here it's the motion in the nominal case, there is no payload. Look here to the tracking errors. It's the joint tracking errors in each joint. Look to the unit, it's a micrometer. Look to the maximum, like 25 micrometer as maximum tracking error. This is the tracking errors, and this is the input torques. There is 6 motors, and you have 6 control inputs. So we have to follow the predefined trajectory that I explained before. Okay, here, and here, nominal case. There is no payload, no external services. Now we tried another scenario where we try to add a payload. And for sure, we suppose that we don't know the payload, the mass and the inertia and so on. So what we did, in this adaptive sliding mode controller, we estimate in real time the mass and the inertia of this payload that has been fixed on the robot. So we will arrive to this. Let me maybe accelerate the video slightly, because if I can, because I cannot maybe. Anyway, it's almost arrived to the second scenario of payload. So here it was a very nice controller and very nice precision of the trajectories tracking. The torques needed here for motors, as you can see, look here, it's less than 2 Newton meter. So it does not need a high torque because there is no payload, you understand? So the torques here, they are not very high. However, when you add a payload, for sure you need a bigger torque in the motors. We added 200 kilograms here as a payload, and we repeat the same scenarios. And since it's an adaptive controller, we have to estimate the parameters. Here, as you can see, the estimated parameters. We follow the trajectories. As you can see, look at the convergence of the estimated parameters here. Here we are estimating the mass. And look, the mass of the moving platform and the payload, it was like 250 kilograms. And it's converged to the right value. And here, it's the center of mass. We estimate also the center of mass. We put the mass, we don't know the center of mass, we can estimate it in real time. And as you can see, the X and Y and Z, I think X and Y and Z, of the position of the center of mass of this added payload. That's it. And also we did another very nice work with them also. Let me explain the objective of this one. This one, suppose that your pararobot is holding a telescope, okay? And your telescope, you have to orient it in this direction, okay? And suppose that your telescope is on a boat, and the boat is moving. It's moving like that, but you have to keep it fixed while the boat is moving. How we did this? So we did what we call stabilization. So we suppose that we have here an IMU that's measuring in real time the motion of the boat, okay? And we use the controller to measure this and compensate this in real time. And this is the result, you will see. So the first para-robot here, it generates the motion of the boat, it simulates the boat. And the second one is the para-robot that holds a telescope here, for instance, to get a specific orientation. You will see the two scenarios, with and without compensation, you will see the difference. If we compensate, we will have something, look here. And compensated, look to the motion of the water, look here, does not move at all. This is compensated, this is non-compensated. Okay, you can see the difference between them. And this was also within the PhD of the same student who designed the adaptive robot slide remote controller. Maybe the last video is control of cable-driven para robots. Here, one of the big problems of a cable-driven para robot is the links are not rigid, they are cables. And in a cable, you have just to pull, you cannot push a cable. And you need to keep the cable all the time under tension like that. This is the moving platform. We put a maximum tension of 400 Mueller. We proposed here a nonlinear model predictive controller, an MPC. We add the constraints on the cables, on tension, and we respect this maximum tension. Even if you have to put a smaller maximum tension, 250, you will see that it works all the time because it respects this saturation, but however, it will reduce the tracking performance, but it keeps the security of the robot and it keeps this maximum tension in the cables. And we compare it with other controllers and so on. So also in the paper, you can find all the details of this controller, and let me conclude this first lecture of today. So the idea was to talk about control of one of complex robotic systems, which are para robots. So they have very high accelerations, high precision applications. So we have two cases, the case non-redundant and actually redundant. We have a lot of challenges in terms of dynamics, operating conditions. We don't know the environment, actuation redundancy, real-time constraints, and so on and so on. And we propose different robust and nonlinear controllers. We implement them, and I show you a lot of experimental results on different experimental platforms. On this topic, I organized also a summer school dedicated to para robots. It means control, optimization, design, everything, all the topics around this. The first edition, it was 2016, 2018, the second edition, the third edition, 2020, but you know what happened in 2020? Yes, COVID, so we canceled this, and now we are preparing the fourth edition. So it will take place between 21st and 25 September. It will be in Montpellier, so if you are interested, you can register and you can come to follow this summer school. So the registration is open until the end of July. With this, let me stop here and let me thank you very much for your attention.
Thank you so much, Ahmed, for your lecture. Actually, it's an interesting topic for a student because more of them are familiar with serial manipulator instead parallel manipulator. So we'll start the question and answer section. Please, if you have a question, raise your hand and say your name and your institution.
Yeah, please.
Hi, I'm Aro from Simestab, and my question is for the manufacturing robots.
Yeah.
Did you use like softer materials, or did you try this on steel or?
The piece to the machining?
Yeah.
A very good question. Yes, it's a very good remark. For sure, the validation that we did, it was on soft material. But the idea was not to, yes, this one for instance, in this video. So it is a soft material, it's something which is not very hard. And here the idea was just to validate the concept, to show that we are able to follow predefined trajectories for machining and to show the concept of machining. However, the robot itself, it can be used to do machine of harder materials.
Yeah,
here it's just validated, of course.
Yeah, but for example, for harder materials, the contact of the tool with the part will produce vibrations and disturbances, and I think it's like the main reason why commercial CNC machines use ball screws in order to don't have that backlash and disturbances. So I was curious about if the proposed controllers may be able to reduce these disturbances produced when machining.
I think you have two things. In our case, we didn't do anything in terms of hardware to prevent these problems of vibrations. This is for sure. This is why we validated on soft materials also. And then, in terms of control, for sure, the control is robust. It tries to manage this interaction to reduce the effects of the vibrations, because our interest here is the precision. We try to reduce the tracking error of this following predefined trajectories, but then we didn't test it, I mean real conditions. For sure it is robust, it should manage this, but at what level, I don't know. If we put like wood, or if you put steel, or if you put copper, I don't know which material we use. We validated on soft material, which is easier, just to show the concept, but for harder materials, we have to make another study in the apply to evaluate first the actual controller, and if it's enough, or not enough, what we can do, you understand? But it's a good question, yes.
Thank you.
Thank you. Yeah, please.
Someone else?
Hello, my name is Luis. I am from Upita. My question is, have you thought about integrating sliding mode control to the MRAC for compensating non-linear dynamics?
Integrating sliding mode with what?
Sliding mode control to the MRAC for compensating non-linear dynamics.
Sliding mode with MRAC. I don't think so. Which, the one that we proposed, or if we tried this?
If you try this.
No.
Have you tried it?
No. No. We combined the sliding mode with some other controllers with adaptive feed forward. I mean, the feed forward, which is based on the dynamic model, and we make it adaptive. We compare it with, we combine it with the sliding mode. But with MRAC, not yet, I guess. I don't, no. But you can look to the papers that I showed you the link by the end. Here on ResearchGate, you can find all the papers. We have one paper we have at least maybe 3 papers on this robot. And for this robot here, for instance, what we proposed is an adaptive sliding mode controller. So we make, but it's not MRAC, understand? So it's the sliding mode that we make it adaptive. So it's possible to combine MRAC with the sliding mode controller, it's possible. Okay. But we didn't do it here.
Okay, thank you.
Thank you.
Someone else?
I have a question.
Yeah, here.
Thank you.
Actually, I have a couple of questions.
Yeah, please.
Yeah. The first one is about the hardware again. My name is Javier Molina from La Salle here.
Yeah.
What about the hardware in high-speed parallel robot? What kind of motor did you use in order to test your experiments? But that's the first question. And the second question is about the. Actually, I'm trying to work in agricultural robots. So at the beginning of the presentation, I saw you that you present a mobile robot with a parallel robot or a delta robot.
Yeah.
You know, in that case,
let me first answer the first question and one by one.
Okay.
So for the first question, yes, it's a very good question. So for this robot, for which, I mean the R4, for which we reach 100 G, very high speed. So the motors are here. So these motors are from Etel. Etel, it's a Switzerland manufacturer, okay? So they are extremely good motors. However, they are very, very, very expensive. Brushless motors. Just to give you an idea, on one of the motors, we had a problem. And we tried to analyze the problem. So the problem coming from the motor. We sent the motor to the manufacturer. So they analyzed, they found that the problem is coming from the encoder. Just the encoder that measures the position. Imagine the price, just of the encoder alone. 3,500 euros, one encoder. And the motor itself, 6,500. You know brushless motors, you can buy them 500 euros, or even less. Those motors, they have the price of 6,500 euros, one motor. Imagine you have 4 here, 26,000 motors, and only 4 motors. So the quality is here. They are very good. They deliver a torque of, I think, more than around 150 Newton meters, something like that. Very high torque, very high precision, very high quality, but the price is very high. Okay? Yes, please, next question.
Thank you. Quite expensive.
Yeah.
It's really possible. But anyway, so the second question is about a more practical application in agricultural robots. So yeah, I'm trying to work in agricultural robots. I think the parallel robot or the delta robot it's a good idea. Yeah, but you know, you present here a lot of control techniques in order to control your parallel robot.
Yeah.
So, but in order to control this kind of parallel or that kind of agricultural robot, is that enough a PID, a simple PID, in order to control that?
Yeah, good question. A good question. I think for such applications, a PID is enough. Okay, because here you are not looking for a very high precision. It's not the case of the robot to 20 micrometer of precision. Here you don't need, because you are in agriculture. I mean, if you are a precision of even less than 1 centimeter, a few millimeters, or 1 centimeter, it's enough. It's okay. So I think a simple controller would be enough. Also, maybe if you are interested, just send me an email. I will send you a link to the company specialized in this, and they designed a mobile robot with a Delta robot. So the company, it's I think in France, and they are developing some solutions. Just have a look to their solutions, maybe.
Thank you very much.
Thanks.
Someone else?
Yeah, please.
My name is Jesus from Cipstar. I have a technical question.
Yeah, please.
When you apply a L1 adaptive control, when you in the Riccati equation, what kind of model will better for the regulator for estimating the delta hat? Because I remember the student writing the sender.
Let's go there, and they will explain, because there is something regarding the model. You are right. Because I didn't detail. First of all, I told you that this is a non-model-based controller. Okay, so it means that you don't need the model to control the robot. But, however, you can see there is a model here. What represents this model? This is the question. The model that you are seeing here, it's not the model of the dynamics of the robot. Okay? And the robot has not a linear model. This is the linear model. You understand? So you have the model of the robot, it will be something like that. Something like that, equal to tau. So this is a nonlinear model. Okay? And here you have the control input. And here, as you can see, you have a state space model, which is here that represents the system. So this model, in fact, you go from this and you choose here a control input to equal something, such that when you replace it here, you get to this model. You do a first feedback, the first nonlinear feedback, to bring this model to this model. Okay? And once you have this model, the tau that you will choose here, pay attention, it's not based on the model. You will not use M and C and so on. It's a feedback that brings you this nonlinear model to this. And this is why, if you pay attention, look, here, AM. AM, it corresponds to this linear model here. So you have a first feedback, brings you from this nonlinear model to this linear model, and you construct your controller based on this linear model. And this linear model, you construct the state predictor. As you can see, it's the same as this one. Okay? And then you estimate the parameters, and you put them in the control loop, a filter, and you close the loop. You understand?
Yes, I understand. When you get the converge, The problem is optimal. So,
It's like an optimization, yes.
Okay, that's right.
You can have a look in the papers. You can find all the details, how we designed the controller. I'm not talking about the book, I'm talking about the papers. Like when I show the, let me go to the experiments where we did this. This is rise. Yes, here. Yes, this paper, for instance. Go inside this paper and you will see step by step how we can get from this nonlinear model to the model used there and how we estimate the parameters.
Thank you.
Another question, guys? About the model, the challenge is obtain the model. No one?
Yeah,
So,
Jorge, yeah, please.
When you particle response in the start, when you estimate the parameters, you suppose they appear in a linear form with respect to the regressor.
Which
is a general property of the robotic systems in general, or because from the theoretical point of view, it's much more interesting when it is non-linear.
Yes, you are right. You are right. Very nice question and remark. Yes, for sure. Most of robotic systems, you know, they suppose that from this model, you suppose that you have certain number of parameters to be estimated, okay? And you rewrite these dynamics in a certain way that you appear, okay, the parameters to be estimated. So if you go back, for instance here, look, this is the representation. It means that this equation can be written as a regressor matrix, so it will be y, depending mainly on q dot, something like that, okay, multiplied by a vector. It can be theta or hat theta. So this is tau equal. So you write this equation like that, and you have the regressor matrix here, which is nonlinear. However, the dynamic model, it's written in affine form. It's a linear form because you have this matrix Y multiplied by the parameters. Most of robotic systems, it's possible to do this. I mean, from the dynamic model, we obtain this. Okay? So in all or most of the applications that I show, this is the case. So it's possible to write it in this form, linear form with the parameters. But it may, I don't know, it may arrive, but most of the time, mechanical systems, this Lagrange dynamic model, it's linear in terms of the parameters. But maybe there are some exceptions. I mean, theoretically you can make it, but physically if there exists a model where when we write this, it's not linear, it's not linear in the parameters. Maybe it's happening, but physical systems, that all the systems that we worked on, all of them, it's linear with respect to the parameters.
This is very good news for.
Yeah, exactly. Very good news for those who want to do experiments. So it's linear with respect to the parameters. Any more questions?
Well, thank you so much, Ahmed, for this lecture. I have the last question about what is the problem or the challenges to implement a fault-tolerant control of this kind of...
Implement what?
Fault-tolerant control.
Fault-tolerant control. Yeah. Good question. I think the challenges may be, first of all, the complexity of the model, and also the procedure that we use for fault-tolerant control. Because fault-tolerant control, for those who don't know, you design a controller and suppose that something happened in the system. Okay, there is a fault somewhere in a sensor, for instance. You get the measurements from an encoder, the encoder is not working, the controller is not working, and you use the performance. How you can manage this issue, this problem? So you design a controller, despite this fault in one part of the system, you continue controlling the system. So what we suggest is, I will show one of fault-tolerant controls in the next lecture. So in the next lecture I will talk about one example of fault-tolerant control in an underwater vehicle where we have 4 actuators and we stop one of them. Deliberately, so we stop one of the actuators and we try to check if with 3 actuators instead of 4, if we continue able to follow the trajectories. And we designed the fault-tolerant control. Yeah.
Thank you.
Be inspired, as I explained in the first lecture, in terms of morphology, in terms of control, in terms of actuation, and so on. So this is a specific class, and a lot of applications can be identified of those vehicles. And then the last class is the class of the ASVs. ASVs is coming from autonomous surface vehicle. These are small vehicles like that, and they stay on the surface and they perform in an autonomous way. And also, those vehicles, you can perform very long-term missions. Why? Because, look here, if you observe what we have here on the surface, solar panels. You can recharge the batteries. What we have also, look, this one. It can be used to recharge the batteries. And you use the wind energy or the solar energy to recharge the batteries, and you can use those vehicles also for a very long time missions. So this is the main classes. Now, if you are interested to do research or industrial applications of those vehicles, we can identify several research topics. One of the topics, the first one, it concerns the perception of the environment, the sensing of the environment. Perception, pay attention, it's not so easy. I mean, if you have a mobile robot on the ground, it's very easy to use satellite, GPS, Wi-Fi, radio, all the signals, they work. However, underwater, nothing is working. Okay, this is a big problem. And also, the conditions of work underwater may be very difficult. Sometimes, look to this picture. The visibility is so bad. So if you use a classical camera, it does not work. You know, actually, I'm working with a company. We will start a new PhD. I will tell you maybe more. So they are specialized in cleaning the dams. The dams, years after years, what happened? So they have, this is a dam, it's here for instance, and then the water is coming from here. And you have water until here. So you have all this quantity of water in the dam, okay? So this is the dam, okay? Now the problem, they told me, years after years, you will have sediments here. And they will have accumulation of sediments up until a point where you will have all these sediments and water, only this. Only this is water and this sediments. So you have a very small amount of water. And this is a big problem. And they propose a solution to remove this, how we can extract these sediments and put them outside, such that you will regain the same size of the dam, you have a lot of water. And one of the problems, they have a strong problem underwater perception. I mean, when they extract these sediments, the visibility is nothing. And even the sonars, cameras, nothing is working. And they try to find a solution, how you can localize the vehicle and how we can resolve the problem. I do not have time, otherwise I can explain more the concept. So we are talking about control and automation of those tasks in these conditions, and it's extremely, extremely difficult. And we want to work in cooperation with them to resolve this problem in terms of perception and autonomous control also. So this is first topic. Also here, just to say, I have a colleague in France, he's working on electrical sensing, okay? So it's like the eels, underwater eels, so they use electricity. The same, he's working on using electricity in vehicles to detect obstacles, to detect other animals and so on. Electrical sensing. So it belongs also to the perception. Also another problem is the problem of localization. You have an underwater vehicle. If you are in a pool, it's very easy just to put a camera and you can see where is your vehicle. However, you are in open water, in the ocean, in the sea, in the lake, it's not easy. GPS is not working and you are underwater, and how you can localize the position of your underwater vehicle. So a lot of people works on the SLAM, simultaneous localization and mapping, and this is very interesting for underwater applications also. Then sometimes you have to combine different kind of vehicles like surface vehicle, aerial vehicle, underwater vehicle, and you need to work on the software. And software, it's also a very interesting research topic in marine robotics. Then we have the classical problem of communication. As I told you, nothing of the signals that you have on Earth, they work underwater. So the most used signal that works very well is acoustic signals, the sound, to use the sound. I will show you by the end of the presentation some experiments where we use the sound to detect a source and to follow the source, to do the tracking of the diver based on a sound signal, acoustic signals. And sometimes also related to the next topic, which is the swarm underwater vehicles. So imagine that you have a group of vehicles, maybe 3 or 4 or 5, and you want to do the coordination of the motion of those vehicles and the communication. So we have the problem of the communication and also the coordination of motion and synchronization. And the last topic, it's the topic that I'm interested in. Whatever your underwater vehicle is, you need to develop a controller, because classical control will not work. Because if you design a PID for most of the applications, due to the environment, due to the operating conditions, due to the complexity, the PID will not work very well. And in this case, you need to develop more sophisticated controllers, and this is why we are interested in this topic. And now, starting from now, let's focus on the control problem formulation. And to introduce the control problem formulation of underwater vehicles, let me show you 2 examples. And these 2 examples, we are doing the underwater inspection. Here it's the inspection of the ship hull, and this is the inspection of the dam. And for both cases here, for both examples, we are using ROVs. And now let me introduce the limitations of ROVs. What is the limitation? What is the drawbacks of using an ROV? As I told you, it's a human who is piloting the underwater vehicle, okay? And there is a cable linking the control system to on the surface to the underwater vehicle. Let me show you the 2 videos, and let me try to emphasize the limitations of this solution. Even if you are using an underwater vehicle, it has a lot of limitations. Look, here's the ship hull, inspection of the ship hull. Look, this is the feedback from the camera on board the vehicle. And look to the quality of motion. It's very oscillating, it's not very stable. So this is the first case. And the second case, we visited this company, it's called EDF. It's the national electricity company in France. It's called EDF, and they did the inspection of this dam using an ROV, as you can see here. This is the human piloting the underwater vehicle. This is the feedback on the camera, on board the vehicle. You can see the dam. Look at the visibility is very bad, and also it's very difficult to control this underwater vehicle because you may have underwater currents. The visibility is not so good, and here they try to look to the surface of the dam and find the places that need intervention, inspection, maintenance. This is the objective of the underwater inspection. So from these 2 examples, what we can notice? We can notice that there are a lot of limitations. One of them, the oscillations. You have seen from the camera on board the vehicle, it's not very stable, and this is a drawback. And this also is related to a lack of precision. So the tracking, the control is not very precise. And pay attention, it's not so easy to get this precision because it's very difficult due to the environment. It's operated in open loop. There is no feedback. The feedback, it's the human who is looking to the screen. He looks to the screen, he turns to the right, to the left. It's the human who has this feedback. But the control system, it has no feedback. And it's difficult to be manipulated, and also it needs a good person with a good experience, and you have to pay him. It's expensive to do. I don't know how much you have to pay a person per day, but it's expensive. So the solution that we may propose in this case is to do automation of those tasks. So in this case, we have to replace the operator by a control system, or at least we can help the operator. We can assist the operator. We keep the operator and we help him. So we have different levels of autonomy. If you want to do something fully manual, it's the human. If you want to do something fully autonomous, you remove the human and replace it by a control system. If you want to do something semi-autonomous, you keep the human, he controls some degrees of freedom, and some other degrees of freedom are controlled by the control system. However, in this case, as I told you, PID controller is not enough. In this case, you need to develop a better controller, and in this case, you will be facing several challenges. And the challenges that you may be facing is that the system itself, as I explained in the first lecture, it's a complex robotic system. Because of the highly nonlinear dynamics, there is a coupling between the degrees of freedom. There is a time-varying parameters, strong uncertainties. You cannot measure everything, like position X and Y of the underwater vehicle, impossible to get it. You have not a sensor to measure it. And so on. All those challenges, you have to deal with them when you design a controller. Nice. Let me show the video that illustrates what I'm talking about. Imagine that you have an underwater vehicle and you want to do a mission. And during this mission, you are interested to control the underwater vehicle. You are controlling the underwater vehicle, you see the environment around, it's very complex, and you may have external disturbances, underwater currents, for instance. These underwater currents, they may disturb the vehicle, the umbilical, or the system. And you need to deal with this in your control design. Also, during the mission, sometimes you need to modify the vehicle. I need one extra sensor to be fixed on the vehicle. I add a camera. This camera will change the mass, the inertia of the vehicle, and so on. And you need to keep the same controller. You need to deal with this. And also, in other situations, you have here something that is fixed on the body of the vehicle that will modify also, like the damping of the vehicle, and you need the controller to manage this. And also, during the mission, also you may have an interaction with the environment, so an impact with the environment, and that this may destabilize the vehicle, and you need to design a controller able to reject this external disturbance in a very simple, in a very performant way, while keeping the stability of the vehicle. So all those aspects need to be taken into account when you design a controller. This is why I told you simple PID may not be the good solution. So we have to manage all these issues. And also pay attention, you have to design one controller. It does not mean that I design a controller here, a nominal case, there is a disturbance, I have to retune the controller. I modify the vehicle, I need to retune the controller. There is a modification, an impact, no. You have to design one controller that should manage all these at once. You have not to retune the controller again, just one time. And this is why it's challenging, and this is why you need to design a good controller. So, the concept that I told you, if you talk about the autonomy, so fully autonomous, fully manual, and semi-autonomous, here we call it like this concept of co-control. It means that we have a human operator, and we have a control system, and they will work together. They will work together. The idea here is that the human using the joystick, for instance, will control X and Y, because we cannot measure X and Y. It's the human who will see the robot and try to control this position. However, all the other degrees of freedom, like the depth, roll, pitch, and yaw, camera, and so on, we can close the loop using those measurements, and we design a controller here. And then here we design the reference trajectories to control the vehicle to make this mission by following the reference trajectories. This is assisting the pilot, or the concept of the co-control. And in many applications, we apply this concept. Now, before I talk about the control schemes that we are developing, let me talk about the experimental platforms. And as I told you from the first lecture, my interest is to do control, but I want to go until the real-time application. So the theory, stability analysis, implementation, and validation real conditions. This is why we need experimental platforms. Here are some of them, let me introduce them sequentially. So first of all, we start with this small vehicle. It's called the Acro. It's a small vehicle, as you can see here. You can see the size. It has a cable. It has 6 propellers, 6 actuators. However, we can control only 5 degrees of freedom. Here, as you can see, the horizontal propellers, they are 4. They can control X, they can control Y, they can control the yaw angle, 3 degrees of freedom. Then we have 2 propellers here, F5, F6. They can control the depth, they can control the pitch. However, the big problem is the roll. The roll, you know, is the angle here around this axis. So this cannot be controlled because all the 2 propellers that are aligned in the middle here. So we can control up to 6 degrees of freedom. This is the hardware of the vehicle, and this is some of the features. So we can go up to 40 meters of maximum depth, 6 propellers, we can control 5 degrees of freedom, and this is the size of this underwater vehicle. Now the second one, after this vehicle, so we started with this, we worked with a PhD student on this vehicle, but the quality was not so good, so then we decided to design our own vehicle. So we designed this vehicle, it's called Leonard, and Leonard has been designed in the lab in the idea of to provide something in which we have the possibility to implement low-level control. So it's an open structure for the control. So we can implement any control we want. And the vehicle itself, it has 1, 2, 3 propellers like that. This is a top view. And with these 3 propellers, we can control depth, we can control the pitch, and we can control also the yaw. The depth, the pitch, and the roll. 3 degrees of freedom with these 3 propellers. This one and this one, these 2 propellers, they can be used to control X and also the yaw angle. So we have 5, and the 6th one is here. This propeller, it can be controlled to control Y. So with this configuration of the actuators, the propellers, we can control up to 6 degrees of freedom. However, pay attention, the big problem in this case, it's not the actuation, it's the measurement. Because among the 6 degrees of freedom, we can measure only 4. We can measure the depth, because we have a 4 depth sensor. However, we cannot measure X and Y. We can measure also roll, pitch, and yaw, because we have IMU inside. So we can roll, pitch, and yaw, and depth, 4 degrees of freedom can be measured, and X and Y, they are not measured. So this is the embedded system for the hardware, and some of the features of the vehicle. We did some experiments where we can go up to 100 of maximum depth. So it was designed to go up to 100 meters of maximum depth. Then, in cooperation with civil staff, within this research lab, it's called LAFMIA, and LAFMIA, it's a French-Mexican research lab. It's like our lab here, but it's situated, it was here in Mexico, and it was managed by CCRS and civil staff, and it was a joint research lab. So in this research lab, so we designed this vehicle, LAFMIA 2, different versions. This is the 2nd version, and it was an AUV, and it was designed with 8 propellers, as you can see here, the different propellers, and we can control up to 5 degrees of freedom, and it was an AUV. So there is no cable that link the vehicle to the surface, and we used it to validate controllers. And here, as you can see, look, the autonomy, it was just 2 hours. I mean, you have the battery which is full, you start, you do some tests, in 2 hours it's empty. So you have to manage this. And some features of the vehicle, we can go up to 20 meters of maximum depth. Then the next one, it was a cooperation with a company, it's called Tecnalia. And Tecnalia, it's a company from Spain, and we cooperate with them on several topics. If you remember Adapt Quattro, you remember the Adapt Quattro robot that he introduced in the previous lectures, which is commercialized in the US. It was a product of our lab in cooperation with this company, Tecnalia. The patent that we made, it was between Lear and Tecnalia. But also they worked on underwater vehicles, and they designed this underwater vehicle. This is the patent, they make a patent. And this underwater vehicle is called Meros. And Meros, it has 2 specificities. First thing, if you look carefully here, so it has a spherical shape. A spherical shape, it's better to move underwater, because you will reduce the effects of the hydrodynamic effect, because it has a good shape. And the other thing, look to the propellers. You have 6 propellers, and look, this and this one, they are in one plane, in this plane. This one and this one in another plane, and this one in 3rd plane. We have 3 planes, and all of them, they have computed the orientation of the planes of each 2 propellers. They have been computed based on optimization, such that we'll optimize the control efforts that push the robot in the different directions. And this is to obtain an omnidirectional underwater vehicle. It means the vehicle is here, whatever the direction you want to go, it's possible. And we distribute the forces that push the vehicle in all the directions the same. So it's a very good solution. And then we show you some of the results. The same, it can go up to 100 meters of maximum depth, 6 propellers, and we can control 6 degrees of freedom. However, in terms of measurement, the same as the previous cases, only 4 degrees of freedom as measured, depth and roll pitch and view, only 4 degrees of freedom. That's it, and now let's talk about another kind of underwater vehicles, because actually all the vehicles that I presented until now, they use this kind of propellers. This is a propeller, a classical thrust. You have a motor and you have the propeller here. You turn, you increase the speed, you increase the thrust, the force that pushes the robot. If you decrease, you decrease. Okay, nice. But now, if we look to the nature and if you look to the sea animals, they do not have propellers like that. What they use to move for underwater, like fish or like a turtle, look to the turtle. So it uses the fins to move underwater. And as you can see, it can move in a very perfect way. And the question that we asked at that time, is it possible to design an underwater vehicle which will be bio-inspired and which will not use the propellers? It will use the fins like the turtle to be able to move underwater. And the solution was the following. So we come up with this design. It was designed in Estonia, in the Center for Biorobotics in Caltech University. And I remember I visited them almost the same time that I visited Civistav here, 2013 maybe. And I visit them and they have seen that they designed this vehicle. And they are looking for solutions in terms of control. So it was the good moment that when they arrived, they have a need in terms of control, and we started cooperating. And now, we started at that time cooperating. Up to now, we are working together. We make, one joint PhD already defended, and 2 PhDs actually are in progress, and 2 research projects, and a lot of visits, a lot of students exchange, and so on. So we started with a simple visit, and we come up with a huge number of cooperation actions. Okay, the same that what I'm doing with Civistav here. So it was a very nice story. So the UCAT, the vehicle is called UCAT, and UCAT, it was designed mainly for underwater inspection. But look here, it's for underwater archaeology. Underwater archaeology, it means that you have a shipwreck and you want to penetrate inside the shipwreck. So you will be very close to the sediments. So if you use classical propeller, you disturb the sediments a lot, and your camera will not see anything. This is one of the reasons that we replace the propellers by the fins. Now, however, this UCAT has strong problems in terms of control. First of all, before they designed the big vehicle, they started with a smaller one. It's called micro UCAT. And this microcat, it has the same structure, as you can see, 4 fins, and the fins are the green parts that you can see here. They are flexible. They are made by silicon. So they made the same robot, but without the same control performance, without the same sensors and actuators, just to see if the concept of using fins will work or no. This just to test. And they test with microcat, and they follow that, it's working, that's nice. Let's construct now the real vehicle. Then they construct the bigger vehicle, UCAT. Now, some of the features, so it is for underwater archaeology. It has some sensors to detect objects. We can identify objects of interest, especially for archaeology, underwater archaeology. It should be small and highly maneuverable. So highly maneuverable, it means it is somewhere, you can turn, you can change the direction very quickly, highly maneuverable. No propellers, so it uses fins, silent motion, and tethered, there is no cable, it's an AUV, and it has 4 fins. The 4 fins is the green part that you can see here, and it is under actuated because 4 fins and 6 degrees of freedom, and even with 4 fins, we'll see it's very complex to be controlled. So there is a very nice control problems for this vehicle. Now, in terms of hardware and equipment, so UCAT is equipped with hydrophones. Why hydrophones? To do what? What is the role of hydrophone?
Sound.
In the human, what to replace the hydrophones in the body of the human? Ears. Hydrophones equal ears. Okay, this is the idea. This is first, and I will show you one application where we use acoustic signals to control UCAT. You will see. And we use those hydrophones. Then it is equipped also with distance sensors. It's equipped with a camera. And also recently we added a DVL on board the vehicle. It has an IMU to measure like the attitude of the vehicle, a depth sensor, pressure sensor, temperature sensor, and so on. We have a buoyancy control system inside, but we never use it. We use the fins to move down, up and down, but we can use control of the buoyancy, a ballast system inside the vehicle. Then in terms of actuation, it has 4 DC brushless molders actuating the 4 fins. And it has buoyancy control that I told you that we never used up to now. So it was a cooperation between our lab in Montpellier with the Center for Biorobotics in Tallinn in Estonia. We started like maybe 13 or 14 years ago cooperating. This is the university, this is the research lab. And then we cooperate within a first small research project. And we get funding to exchange students and to work together. And after this project, we make a first joint PhD, and then now we have 2 other PhDs, and we are continue working together. Now, the question in terms of control, we have several control issues. The first one, the propellers. How we can compare propellers to fins? Look, this is our underwater vehicle, Leonard, and you are moving down near the harbor. Look here. This propeller, look at the sediments, disturbance, look. You can see nothing. And this is to demonstrate that for underwater vehicles using propellers, this may be a big issue. This is maybe a big issue. And then if you use fins, you can be very close to the bottom and you don't disturb the sediment. Look here, demonstration using UCAT. The 4 fins are here. We are very close to the bottom, and there is no disturbance of sediment. The visibility itself, it was bad from the beginning, but we are not disturbing the sediment. Then, second control issue. So for UCAT, if you want to control the motion, you have to use the fins. Let me explain what is the problem here regarding the control using the fins. Suppose that you want to move along x-axis. This is surge, x. I want to move like that. What I have to do? Something like that. This is the fins. I will orient them like that and move. So there is an oscillation, there is an amplitude and the frequency. And based on this oscillation, I will push the robot in this direction. So it means something like that. If I want to move back, something like that. I want to move down, something like that. I want to move out, something like that. So this is the illustration of the different degrees of freedom. X, Z, Y, and the 3 angles, roll, pitch, and U. However, the big question that may be asked now, if I tell you I want to move along X and Y and Z at the same time, how we will orient the fins? And how will we control the fins? So if you want to control more than 1 degree of freedom, it becomes very, very difficult. So this is the big problem. Then the third control issue, it's in terms of model. So we know the model of an underwater vehicle, it's not very difficult. However, the big problem is the model of the fins. Modeling the fin, because it's flexible, you may have a good model, but it may be extremely complex. If you use finite element method, because it's flexible, you will obtain a very complex model that cannot be implemented in real time. And this is one of the big challenges. So you have to choose a compromise between complexity and also feasibility or implementability. So the model should be something like that. Here, what you see F, the big F here, is the thrust. You generate the thrust when you do something like the propeller, when you turn, you generate the thrust. The same here, and it depends on AI. A is the amplitude of the oscillation. In terms of control, if you want to control the thrust, you have 2 parameters. I want more thrust. I am oscillating. I can increase what? I can increase the frequency. I keep the same amplitude, but the frequency, this is small frequency, this is high frequency. I increase the thrust. If I want to increase thrust, it can be the same frequency, but I increase the amplitude. This is small amplitude, this is a big amplitude, I have big thrust. And you can combine both of them. So in our case, what we suppose that we will fix the frequency and we will increase the amplitude. And we use the amplitude as a control input. We did an experiment on just one feed. Look what we obtained here. This is the measurement. The blue one is the thrust. okay, generated by the fin. And here it's the time. And what we changed here, it's the amplitude. So if you increase the amplitude or decrease the amplitude, you will increase the thrust. So we did experiments for different situations, and we took different points. Look here the amplitude: 10, 20, 30, 40, 50, 60 degrees. Okay? And here the frequency: 0.5, 1, 1.4, and so on. And look the red curve here, 2 hertz. This is the fixed frequency. And if you increase the amplitude, you increase the thrust. And we use this as a control input. And in terms of model, we try to find a compromise, simplified model. It's not a big complex one, it's a simple one. We invert this model, and here you have the amplitude in terms of thrust. So it means I want a specific thrust, 10. You replace 10 square, you can use this, you obtain the amplitude that will give you the thrust of 10, you understand? And so on. And we use this. This is a control issue. The fourth control issue, you have 4 fins. It's related to the orientation of the fins and how you will move the robot. Actually, we have 2 control modes, and one of the control modes is called the hover mode, and the second one is called the cruise mode. What is the difference between them? It's look the orientation of the fins. This is the front of the vehicle, this is the rear of the vehicle, this is the front of the vehicle, this is the rear of the vehicle. Look, I want to move in this direction, in X direction. I orient all the 4 fins like that, backwards, to push the robot in this direction. It means you have a big force pushing the robot in this direction. So the cruise mode, it's more used to move from one point to another. It's very performant. And now the question, this hover mode, it's used for what? It's used if you are doing like a dam inspection and you want to follow a trajectory like that. Let me show you an example, and I will tell you why the hover mode in this case will be very nice solution, and it will be much better than the cruise mode. Suppose that this is the surface, this is the wall of the dam that you want to do the inspection, and you want to do something like that. Move like that, okay, like that, and like that. So by moving down and then to the right, down to the left, and so on. And here, suppose there is a problem here, you detect the problem, and you want to stay here. Impossible to do it using the cruise mode. But the hover mode is possible. The hover mode, you go down, you arrive here, you want to stay here, you can stay. It's possible. You know why? Because here, the 2 fins, the front and the rear fins, they compensate each other. And you can stay in a stable position. This is why this hover mode is more appropriate for this kind of task. However, for this one, it's more performant. You have bigger force to push the robot forwards. Nice, let's go ahead. Now, if you are in the hover mode, as you can see here, you can control all the 6 degrees of freedom. You can control the surge, the sway, the height, heave, and the roll, pitch, and yaw. However, if you are in the cruise mode, you cannot control the Y. You control 5 degrees of freedom. It's impossible to control the Y due to the configuration of the fins and due to the force generated by the... Whatever the configuration you do, you cannot control the sway, the Y. However, the others, they can be controlled. Nice. Now let's talk about the control solutions. And if we look, if you want to have a look about the literature or the state of the art concerning the control of underwater vehicles, we can make this classification. This is one of my former PhD students who did this classification. So the control schemes, they can be classified in classical control scheme like PID, like robust control scheme like sliding mode control, adaptive control schemes like adaptive computed torque, intelligent control schemes like fuzzy logic control, hybrid control schemes like you combine fuzzy logic with PID, and other control schemes like model predictive control. So these are all the classes of controllers that we can find in the state of the art, and then for each of these classes we can distinguish, look, non-model based, model based, non-model based, model based. Non-model based, this means that you don't need the model to design your controller, but model based, you need a model. This is the difference, and for all of them we have model based and non-model based. You can find more details in this paper that we published. It's a survey paper on control of underwater vehicles, and you find a lot of controllers. We select some of them, we implement them, we test them, and we compare them. So it's a survey paper that we published in annual reviews of control. Now, the proposed controllers for the vehicles using propellers, classical propellers, we designed, like we started with the PIDs, the step 0, it's the level controller, and then we start developing a lot of controllers, nonlinear, adaptive, rise, sliding mode, and so on and so on. And now, for most of the controllers, especially if you want to start with simulation, you need a dynamic model. And for the dynamic model, it's not like robotic manipulators. You apply Lagrange and you find your dynamic model that can be used for simulation. Here, for underwater vehicle, as I told you, remember the first lecture I told you, what is the difference between robotic manipulators and mobile robots? Mobile robots, robotic manipulators, they have a base which is fixed. Mobile robots, the base can move underwater, aerial, on the ground. This is the difference. And this is the example for underwater, the vehicle can move. In this case, we have to define two frames. The reference frame one is called the air fixed frame. This you can put it, it's fixed, and it is situated on the surface, and it does not move, okay? And the second frame, it's fixed on the body of the vehicle, and most of the time, we would put it in the center of gravity or the center of volume, and when the vehicle moves, this frame moves with the vehicle. And then we can compute the position of this frame with respect to this frame. And then we can do the transformation from one frame to the other. Then the different variables needed for an underwater vehicle modeling, since the vehicle it is an object like that, so it has 6 degrees of freedom, X, Y, Z, and 3 angles. So the 6 degrees of freedom, they are here. So we call them the position, 3 degrees of freedom, and the orientation. So we have X, Y, Z, and we have K, M, N. So this is the forces and moment. This is forces, this is the moment. And the degrees of freedom, they are called X, Y, Z, so the surge, sway, and heave, and then you have roll, pitch, and yaw. So this is the forces, this is the degree of freedom itself, this is the velocity, u1 and u2. But pay attention, these velocities are not in the air fixed frame, they are expressed here in the body fixed frame. So these are in the body fixed frame, and this is the position and orientation, X, Y, Z, and the angles, roll, pitch, yaw, so phi, theta, and psi. We have 6 degrees of freedom, and these position 6 degrees of freedom, they are expressed, pay attention, in the air fixed frame. Pay attention. This is air fixed frame, this is body fixed frame. Then we have to find the kinematics, and the kinematic modeling it help you to move from one frame to the another, from the body fixed frame to the air fixed frame. So we have this equation. Remember here nu, it was what? It was the speeds in the body fixed frame. And eta, it was what? It was here eta 1, eta 2, it's eta. It's the position in the air fixed frame. So if you compute the derivative here, you obtain the speed in the air fixed frame, which is equal eta dot here. However, you need to use the Jacobian matrix or transformation matrix multiplied by the speed in the body fixed frame to obtain the speed in the air fixed frame. So this is the kinematics, and this is the definition of this Jacobian matrix G here. Then we have to use or to compute also the dynamics. It's like a robotic manipulators. Look at the dynamics here. We have here the term of the inertia, Coriolis, damping, gravity, and control inputs and external disturbances, with the definition of all the terms. It's like a robotic manipulator, but slightly different, because for instance, if you see the inertia matrix, a robotic manipulator, you take just the inertia. However, for underwater vehicle, you take the inertia, but you take the added mass. What is the added mass effect? Look, I'm walking here, I move my legs in a very easy way. If you ask me to go inside the pool and try to move, it will be more difficult. Why? Because there is a liquid, there is a water surrounding me. So when I try to move my leg, I feel that my leg is heavier. And this justifies this term that we call it added mass. It's like the volume of water that you remove when you put your leg inside the wall. So we consider this effect of the added mass in the different terms, in the inertia matrix, in the Coriolis, in damping, and so on. So, and all the matrices, they are 6 by 6 because we have a system of 6 degrees of freedom. The control input is tau here, and it's a vector of 3 forces and 3 torques because you have x, y, z, and you have 3 angles. Now, if we want to design a controller, for sure, you have to think about the architecture of your control design. And mainly, when we design a controller, the objective is to follow something. Like for boats, imagine that you have a boat, you arrive to a certain place, and you want to stay there. If you cut the motors, you stop all the motors of the boat, what happens? Then you will be adrift because currents, so the boat will move. If you want to stay at exactly the position where you are, what we call this DP, dynamic positioning. You try to use the propellers, the actuator of the boat, such that you stay there. This is called DP, and the desired value, it's a constant value of this position. So here, you try to control something where you have a constant desired position. However, sometimes you have to follow predefined trajectory, so the reference should be something which will be time varying. How we design, how we generate what we desire as a reference is in this block, and this block is called the guidance system. So a guidance system in an underwater vehicle, it's a block that generates the reference trajectories for your vehicle depending on the task. I want to follow predefined trajectory, I want to stay in a specific position, what I want to do exactly. Then this block of guidance, it will generate the reference trajectory that goes to the controller. Here you have the most important block which represents the control. If you design a PID control, you put it here. If you design a sliding mode control, you will put it here. So, and this block, it gets the measurement, you have a feedback here, you get the measurement, you get the reference, you compute the errors, and try to generate the control actions to follow the desired trajectories, depending on the mission. However, now, how you will get the measurements? You need something else, which is here, it's the navigation system. Imagine that you are here in Mexico and I ask you to go to Monterrey and you will use your car and you don't know the road. You put a GPS and the GPS in real time will help you to follow the path. So it's a navigation system. So here it's the same. It's a group of sensors that can be used or estimated. It can be a state estimator or a sensor that can be used to have this feedback about the state of the vehicle and the environment. And if you combine all of them, the guidance system, the control system, and the navigation system, you will obtain the control architecture including all of them. And this control architecture may be implemented for any underwater vehicle, surface vehicle, a boat, a ship, whatever. Okay? Nice. Now let me introduce some control solutions. For sure, as I told you, I will not have time to develop or to detail all the controllers that we did. What I suggest you is go please on ResearchGate, get the papers, and you will have all the details of several controls. But let me introduce at least 2 or 3 controllers to show you how we design a controller for an underwater vehicle. Let's start with the basics, PID controller. And the starting point is this. The first here is the dynamic model, this is the kinematic model. Kinematics and dynamics. And I want to design a PID controller. And the PID controller is designed in the air-fixed frame. And in the dynamic model, as you can see here, it's written in both spaces because actually you have, look here, it's EDA, it's the air-fixed frame. This is the body fixed frame, body fixed frame, body fixed frame, air-fixed frame. So you have to manage to rewrite your dynamic model just in one space, okay? To write it in the air-fixed frame. To this end, what you have to do, you take the kinematic here model and you compute the derivative. This is a speed, this is a speed, this is Jacobi matrix. If I compute the time derivative of this equation, I obtain what? What is the derivative of speed? Acceleration. So this is the acceleration in the air-fixed frame. This is the acceleration in the body-fixed frame. This is the derivative of Jacobi and so on. You obtain this expression, and based on this expression, what you have to do the inverse. It means you will compute in u dot the acceleration in the body fixed frame in terms of the acceleration in the air fixed frame, like that. And you replace this in this first equation, and you come up with this equation that represents the dynamics in the air fixed frame. With the definition, look to the all the matrices used in this dynamic model. So you will use this dynamic model to design tau here, your control input. So you should put here a PID. What is the PID? How it is can be controlled? How it's been designed? Sorry, it's like that. This is tau PID, proportional integral derivative. However, pay attention. Why I multiplied here PID by the Jacobian matrix transport? Why? Do you know? Do you have an idea? Why didn't it put directly this expression? Huh? We changed already this frame here. Here we changed we obtained this. When we change the frame, we obtain this. And what we obtain in this equation, what do you remark here? We have G minus T. It means you have to multiply by GT to obtain identity. You understand? This is why we put here in the PID this term. Okay? And this is the final expression, and this is the block diagram of the proposed PID controller. So it's not very complex, it's easy, but it has a limited performance. So this is the first controller. The second controller that I want to show you, this is general. It can be applied to any system. It's not specific to Android one. But I want to show you this one because maybe most of you here, you know PID, but you don't know nonlinear PID. So PID, it has three gains here, Kp, Ki, and Kd, and all of them, they are constants. So you can design a nonlinear PID where the gains are time varying. I explained in the previous lecture the case of using time varying gains like that. So this is the idea of nonlinear feedback gains. So you can use it here to tune or to choose the nonlinear feedback gains, proportional, integral, derivative, and this is the idea. You start with a controller where Kp and Kd, they are constants, and the idea is to make them time varying. And this is what you will gain. So you'll have better performance, better convergence, and better controller. This is the two gains, proportional and derivative. I explained before, you will change one controller, one parameter to be tuned by three gains, because here you have three alpha, delta, and Kp. And here, the nonlinear gains will have a large gain for small error. Here, as you can see, it's large. Then for a big error, you have a small gain, and then you can increase exponentially. And here, once you reach this threshold called delta, you keep the gain constant. Because if you continue growing, you will go to infinity, and this is not good. Understand? This is why we saturate the gain here, and the same for Kd. And here, the benefits. You will have a good transition, a good damping, and a good robustness. Let me compare both gains. If you take Kp multiplied by E, and here E is the position error. This is the Kp multiplied by the position error. Linear case, you will have something like that. Okay? But the nonlinear case, here within the delta, it will be constant, because you are here it's constant, so it will be linear. And here it will be exponential, it's non-linear. This is the difference between linear and non-linear gains. And now I give you just an illustration on a very simple example of mechanical system. It's a mass damper spring system. And the idea is to do the control of this system using linear and non-linear PD controller. So I designed like two controllers, linear and non-linear. You have the parameters. Non-linear one is here. The expression of the two gains is here, the parameters, they are here, and this is the expression of the different functions used here. And look to the results and compare by yourself. Look here, the blue one is the linear PD, and the green one is the nonlinear PD. The performance is better, since here you have a convergence, it's more stable, here you have oscillations, you have less oscillations, and the good thing is that we have a better performance with a better energy, because here you will spend less energy than the linear one. So you obtain the performance and you reduce the energy. This is why nonlinear PD is better than the linear one. Now we can propose a model-based controller. It's called nonlinear PD+. You know PD+ controller or no? it's like a PD, and the plus it's like a feed forward. And the basic idea is the following. Here we take the same expression of the dynamic model, the kinematics, we compute the derivative, and we obtain this model that represents the dynamics in the air fixed range, like the previous one, like the PID. And look to the control design. This is the PD plus controller. It has here PD, proportional derivative, and this is the dynamics. Look, M, C, D, G. So it's exactly copy-paste of the dynamics that you are here. You want to compensate it. So you do copy-paste. However, what is difference in the PD plus? Look, here in the you have eta dot, and eta double dot. And in the control, eta double dot D, eta dot D, eta dot D. So we replace the derivative speed and acceleration by the desired ones to reduce the effects of the noise, and that's all. So copy-paste of the dynamics, we replace the derivative speed acceleration by the desired ones, and you add here proportional derivative. And here it's a nonlinear one because Kp and Kd, they are nonlinear, they are time varying, they are like the what I have just shown you here. They are like that, okay? Nice. And this is the nonlinear PD plus, the concept, the control law, and this is the how the gains are modified, Kp and Kd, how they are time varying. Now concerning the UCAT, concerning the bio-inspired underwater vehicles, we develop other kind of controllers. Here are some of them. First of all, we start thinking about the problem of ender actuation. 4 fins, 6 degrees of freedom. I want to control more than 1 degree of freedom. How I can proceed? So we start first developing controllers, blocks of controllers, like PD, PID, nonlinear, adaptive, and so on, to control 1 degree of freedom. Then we start applying to 1 degree of freedom. Then we start to thinking about more than 1 degree, 2 or 3 or 4. So we develop the priority-based control. Then we try to use the sensors on board the vehicle. So we apply those controllers combined with the priority-based control, use acoustic-based feedback, vision-based feedback, data fusion feedback, and fault tolerant control. So we try to use first the acoustic signal, the hydrophones, remember what I told you. Then we chose the camera to control the vehicle. Then we did the data fusion between the camera and the acoustic signal. And finally, we developed a fault tolerant control. So I will show you all this. We validate on a simulator like that. Then we validate in a pool, in a controlled environment, which is easy. And then we try to validate in open water in more difficult situations. And we try some situations where we enable kids to swim near your cat, just to show that it's human-friendly, and you can even touch your cat during the motion. There is no risk for the human. Anyway, let me now show you the last part concerning the real-time experiments, and I will show you a lot of videos for control of propeller-based controllers and also bio-inspired UCAT underwater vehicle. Here just it's nonlinear PD control that I just explained. The tracking of the depth and the yaw. This is the control inputs that's used to track this. It's a red curve here, maybe you cannot see it, but it's the desired one. And we are tracking this reference. This is the control input for the depth, for the yaw also. So we start from the surface, we go down, return back, we go up and so on. So these are the trajectories. This is the PD plus controller, and this is nonlinear PD plus controller. It means it's exactly the same controller, the PD plus controller. The only difference, it's exactly this controller. The only difference between them is here. In the PD plus, they are constants, Kp, Kd, okay? And in the nonlinear PD plus, they are time varying. They are like that. That's what I explained before. And if you compare the performance, look to the performance of both. So here, this is the PD plus, and this is the linear PD plus. This is the root mean square error tracking error for both depth and yaw, and 75% of improvement of the performance of the tracking compared to the PD plus, and 64% of improvement for the yaw compared to the PD plus. This shows you the importance of a better controller. Then we tested another scenario. It's a robustness test. We suppose that we modify the buoyancy of the vehicle. Look, we attach two floaters here, 2 grams floaters. We modify by 330%. The buoyancy has been changed. And we attach this sheet that you can see here, we modify by 90% the damping. However, pay attention, we have not to retune the controller. We keep exactly the controller as it is. We don't touch the controller. Here is to test if the controller is able to manage this variation, this change in the parameters, if he is robust. This is a test of robustness. And this is the obtained results. This is the PD plus controller, and this is the non-linear PD plus controller. And by yourself, look, tracking is better here or here? Here is better. Without computation, look, here we are closer than here, and here also. And if you compute, you obtain the values. And also 73% and 57% of improvement. A short video to show the scenario, what happened in this case, and how it works. So we did this in a pool. I don't know if it will start or no. So we did in a pool, and we control depth and DO, 2 degrees of freedom, and we will see. I don't know why. Okay, now it works. Oh, so it's coming. It's coming out, yes. So nominal case first, so we start from the surface, and we try to follow the predefined trajectories of the depth and DO. From the surface we go down, as you can see here, we change the depth. So 30 centimeters of depth and minus 30 of the DO. And then we turn here. When you go down, we turn from 30 to minus 30. And then we turn back and we go up to the surface. And we compare the two controllers, the PD plus and the nonlinear PD plus controllers. Okay, nice. Then here is the annual adaptive control. We test it on this underwater vehicle aircraft for 1 degree of freedom. We control just depth, and we try different situations. This is the nominal case. This is increased floatability. So we attach a floater here to increase the buoyancy to test the robustness of the controller. And we can see that the convergence is very stable in both cases. And we have another scenario where in real time we remove the ball. Look, we remove the ball and we change the buoyancy in real time. So it goes away and then it goes back. So the controller in real time, you know, he is estimating the buoyancy, because the L1 adaptive controller is able to estimate the buoyancy. So in real time, we cut the ball, we remove the ball, he detects that the buoyancy changes, he estimates the new buoyancy, and he compensates it. And this is what we obtain. Then we apply an external disturbance, small, medium, big, and strong. And for all the 4 cases, the controller is able to bring back the vehicle around the desired depth. Here, except the last one, it takes more time. All the others, quickly we go back around trajectories. Here it takes more time because it was very strong external disturbances. And then we try also another, look here, external disturbance, we move the tether. You know why we did this scenario of moving tether? Because the vehicle itself, I told you, it's small. So the tether, it has a big effect on the vehicle, because if it was big, it has less effect. And here we generate waves, and we try to affect, so both the umbilical, the cable, and the robot. And as you can see, look here, the depth, it's constant. So it's very, very stable. Nice, let's go ahead. We test then on Leonard, which is here. This is in the sea, in the harbor. And you will see here the validation of the co-control concept. As you can see here, the depth and the yaw, the depth and the yaw is controlled autonomously with the controller. And the human has just to control the surge and the sway. Has to move backward, forward, and so on. Look here, very stable feedback from the camera on board. And we will see, like here, the inspection of the propeller of the boat. So we'll try to go closer to the propeller of the boat and to get the feedback using the camera on board. So look here, this is the propeller of the ship. Next, here we try to do something which is very important. I explained you the dam inspection. Look, this is surface, I should do something like that. Go down like that. But if you control by view, you have seen the videos that I show you when I talk about the formulation of the control problem, it was very unstable. So here in this case, what we did, we used two cameras, stereo vision. We estimate the depth between the robot and the wall of the dam, and the human has just to push a joystick to move in y direction. And the depth and the orientation, the distance between the robot and the wall of the dam was autonomously controlled. And you see the performance, it's amazing, it's really very nice. A desired distance of 50 centimeters. Look, the depth, the U, and the distance autonomously controlled. Human had just to control the U. Why? To move like that, along this direction, from the right to the left. Here, look. All the other degrees field are autonomously controlled. And as you see, it's very, very stable, here control in this case. Then we change, here the design is 30 centimeters. You have the lighting system and this is the wall of the dam that you want to do the inspection, and you can see the obtained results. Quickly, here we did like saturated based nonlinear depth controller. Here the depth and the U, also different scenarios. We test this in the pool. Nominal case, as you can see, we go from the surface, we follow predefined trajectories on the depth and the U, and then we go back to the surface. And we did this in the pool. In the paper here, mechatronics, you can see all the details of the controllers. I have something to say here. In all the lectures, we talk about control, we talk about theory, we talk about experiment, but I forget to tell you something. Theoretical stability analysis. Up to now, I didn't talk about this. Pay attention, in all the controllers that I'm presenting, there is a theory behind this to study the stability analysis, to prove that the proposed controller, in closed loop, it will be stable. And most of the time, we use Lyapunov techniques to prove this. So if you go through the papers, inside the papers, you can find all the theory behind the stability analysis of the resulting closed loop system. Let's move to the next one. Here we designed an adaptive sliding mode controller. And also the same, we tested in the pool, 2 degrees of freedom, the depth and the U. We try to follow the reference trajectories. And here we will demonstrate the effect of external disturbances. Look, here we start. We follow this trajectory in red for the depth, and this one for the U, and look at the performance of the tracking for both. Here we try to follow it. Look here, a small overshoot here. Look here, the disturbance. We use a stick to push the robot, we disturb it. Look here, the effect of the disturbance. We go away, and then it goes back quickly around the desired trajectory. Once we reach the trajectory, look here again, second disturbance, and so on. And we repeat external disturbances. At each time, if you see carefully, there is a stick. We push using a stick here, look, and look to the effect of the tracking. And the tracking is very nice. We have a convergence, and we continue following the desired trajectory. Here, Miros, it's the vehicle with a spherical shape, just a demonstration with the concept of co-control. So we see how it works. As you can see, this is the umbilical and how it moves. This was in the pool of the university. It's able to follow a surface like that, or even like that, even inclined surface like that. It's possible to do the tracking of this. And this is just an illustration of the co-control. And as I told you, X and Y, they are not automatically controlled because we have not to measure them. It's the human who control these 2 degrees of freedom. It has a lighting system, and it can be used for mostly for inspection tasks. Nice, let's move the next one. Now, UCAT. You will see UCAT is different from the previous vehicles because it will use the fins. You know, at the first time I started working with Estonia on this topic, here it was the status of the control system. Look at it, at the performance, and tell me if they are good or no. Here, without my intervention, they started with open loop control, and it's a human using a joystick controlling the underwater vehicle. And look to the performance, and look to how the vehicle is swimming. So it uses the fins to move underwater. However, they have a strong problem regarding the control of the fins, because they are controlled by the human using a joystick, and you will see the obtained results. Now it orients the fins and start motion. Look, Look here, the video, it's not stable. Look, the vehicle when it moves like that. And do you know why? Because you have two fins, the left and the right, and they are not synchronized. This is why it creates the body, the roll on the body. You know the helicopter. The helicopter, sometimes some helicopters, you know, it's something like that. Okay? And you have here this one, and here they put this one. Why they put this one? You know why? Because if they don't put this one, there is effect of this one, the body of the helicopter will turn. To compensate the effect of this one, they put this propeller to compensate this one. Here it's the same idea. There is no cooperation, there is no synchronization between the right and the left fins. This is why it's not stable in the road. Look here, the operator controlling the UCAT underwater vehicle using the joystick. And then you can see here that they are flexible fins. You can see the flexibility, you can see the motion is not very stable. Then at that time we start working together, and I start proposing controllers, and the first time we start to control 1 degree of freedom and just the depth. And look to the results. This is in the pool. Look the synchronization of the fins, the right and left, and look the stability of the body. It's very stable, and it moves up and down in a very stable way. And this is using just the BID controller to start with, and we were controlling just 1 degree of freedom. Then we try in a more complex environment. Now we try to take UCAT and go in open water. Look here, it was in a lake. Look at the complexity, the environment. You have waves, you will see the visibility is very bad. You have wind, you have waves, you have currents, and all the problems they are here. This is why I told you at the first lecture, there is a big gap between simulation and experiments. Because here in real, look here to the visibility in the lake. It was very, very bad. Just to let you know, look here, there is a small wire, small cable here. Pay attention, it's not the umbilical. Huh? It's just a simple wire for two things. To avoid losing UCAT and also to disturb UCAT. We go until the desired depth. Here we move down like that, we move up like that. When we arrive around the desired depth, the fins are like that. It means the tracking error is close to 0. Here I go down, I go up, I stay where I am. Now look, I use this wire to disturb the vehicle, to pull the vehicle to the surface, then I release it again. When we release, automatically the controller tries to control the vehicle to go back around the desired value. And here we are very close to the bottom and there is no disturbance of the sediments. Then we try here the concept of the co-control, and here it's to obtain the results. We ask the human to control dash the surge, and the other degrees of freedom are controlled automatically. And you know, we try to follow predefined trajectory, like that. And here, manual mode, depth autopilot, and depth and due autopilot. It means fully manual, fully autonomous, semi-autonomous. Fully manual, the human will control 3 degrees of freedom. He should go until the desired depth of 1 meter. And he should keep this depth constant. Keep the vehicle at this depth. And he should control here the U angle. Move like that, turn, move like that to follow this trajectory. And then, so he controls the depth, the U, and also the surge, X. And this is to obtain the result for fully manual. Now, then, in the second scenario, we ask the human to control just the U and the surge. So the depth is automatically controlled. Look, and there is an improvement of the tracking. Here it's better. And it's enabled the human to do better also. The tracking is better of the U. And this is better. Look, they're fully autonomous. Here it's better, and here it's better. Both tracking as better. Nice, and this is just here the priority functions that we used. We repeat the same scenario with and without, and just to show that with those functions the tracking is better. Nice, then we try to use acoustic control. We try to use the 3 hydrophones here, but we want to do something in cooperation with the diver. But the diver will not ask the UCAT, come follow me. No, what we did, so we used a pinger. This is a pinger. It emits acoustic signals, beep, beep, beep. And the vehicle used the hydrophones to get this sound and try to follow the sound. And how we imagine a cooperation between UCAT and the diver? We ask the diver to put here the finger and move, and UCAT will follow in an autonomous way the diver. And this is the illustration for the same experiments in the lake. Look here. The diver is moving, this finger is here, and UCAT in real time, look, it's controlling the yaw, correcting the yaw, and following the diver in real time. And here we can see diver is moving, UCAT is following, diver is moving, and UCAT is following the diver in real time. This was a cooperation based on acoustic feedback that illustrates the cooperation between UCAT and the diver. So this is the first scenario. Then we try another scenario. Now just the camera. We try to follow a target. The target is another vehicle moving, and this UCAT using just the camera to follow this moving underwater vehicle. And the most difficult, the field of view is something like that. If the first vehicle is turning to the right or the left, we can lose it very easily if it is outside the field of view. This is why the controller of UCAT should be very reactive. At the first time the first vehicle starts turning, he should turn quickly to follow the vehicle and to avoid losing the vehicle as a target. And it was successful result, as you can see here. Then we try to think about something else, because both controllers, both measurements, they have limitations. What is the limitation of the finger, of the acoustic signal? This is the finger. When you reach the finger, we continue rotating around. It's not very precise. This is the drawback of the finger. What is the drawback of the camera? If the diver is behind, I cannot see. The camera is like that, it's there. I cannot see. So this is why we proposed another solution based on data fusion between the finger, the acoustic signal, and the camera. And in this paper you can find the details, and this is the video that shows you also a cooperation between UCAT and the diver in different situations. So we repeat the scenario where we use just the visual tracking, then acoustic tracking, then data fusion. This is the visual tracking. If the diver is outside the field of view, we cannot do anything, and we stop the experiment. Look, this is the diver here, and UCAT is here, and once the diver is moving outside, leaves the field of view of the camera, we have to stop. We have nothing. We cannot continue. And this is the drawback of the camera, of using the visual sensor. And then we try another scenario where we use the acoustic tracking. And here for the acoustic tracking, we use a fixed finger. Finger is here, it's not moving. It's like just we hold the finger like that. And we start from somewhere, and the vehicle should converge to the finger. However, when we arrive to this source of acoustic signal, the finger, the vehicle continues turning around because it's not stable. Then we did the data fusion. We start from here, and we reach the finger. And the idea is, if I see the target, I will rely on the camera and the acoustic signal together. We do the data fusion. If I lose the camera, I cannot see the target, I will rely only on the finger, acoustic signal. And you will see it works very fine. Here when we reach the finger, since we see the finger, we use the camera, it's very stable, we reach the finger and we stop there. And then we try the last scenario, a dynamic tracking of the diver. Here, look, the diver is moving and UCAT is following the diver. If he can see the diver, you will use the camera and the finger. If he cannot see, it's behind or it's moved quickly to the right or to the left, in this case, he will rely just on the finger. Now the question is, how he can detect the diver? And the answer is, we use deep learning algorithm. We train this algorithm using a lot of videos from the web of divers, and we use this here, and in real time, if he sees the diver, if it is a diver, the algorithm will say, this is a diver. He will use it as a reference and try to follow the diver. So it was successful. And the last scenario, last video, it's the fault-tolerant control. We try to stop one of the fins. Instead of 4, we will use 3, and we test if it is able to follow the predefined trajectories. Let me show you, the video, and it will be the last one. Yes. Fine. here PID control, sliding mode control, and here all the fins, they are healthy. So we are using all the fins. Look here to the tags in the floor. You know for which purpose we are using the tags here? Do you know? Try to think. Not for the vision. For what? Yes, nice. For X and Y. Remember, we cannot measure X and Y. We can use the camera and these tags to have the X and Y position real time of the vehicle. Since we try to follow elliptical trajectory here, elliptical trajectory to be followed on X and Y and the depth also. Then now fault current control using the PID controller, and we have 4 cases depending on which field we will stop. Here like the right, the rear left, the front left, and the rear right and front right. And for among the 3 scenarios, this one is the more difficult. Look, it's stuck in the middle and the controller is not able to follow the reference trajectories. Because the effect, if you stop the right or the left, the rear or or the front, it's not the same effect on the tracking of the reference trajectories. And we repeat the same scenario now for the sliding mode controller, and we can see the performance. And here it's better than the PID for sure, especially for the 4th case here. It's better than PID where the vehicle stuck in the middle. Nice, that's it. This is the last slide. In the papers you can find all the details regarding the controllers, regarding the performance, the theory, and so on and so on. That's it, and for the conclusion, so the idea of this lecture was to introduce one of the complex robotic systems, especially autonomous underwater vehicles, and their control problem. I introduced general context, mainly for underwater inspection or archaeology, the different associated challenges as complex robotic systems, the proposed different control solutions, and especially the validation in real-time experiments for 2 kinds of vehicles, for small tethered autonomous underwater vehicles using propellers, and for bio-inspired AUV, which is a turtle bio-inspired underwater vehicle UCAT. So you have seen a lot of scenarios and a lot of videos. And to finish, the same as the previous lectures, all the papers, they are here, you can download them. If you have any problem or any problem to get the paper, just let me know, I can send you the paper. And that's it, let's stop here for this lecture, and let me thank you very much for your attention.
And remember, today is the last lecture for the suspension activities at La Salle. Also, we spend more time than we spent for this session, so we time for 1 question. From one else?
One question, yeah, please.
Thank you. If you want, I can start this.
Please.
Thank you.
Your name?
Thanks. My name is Rafael Sanazaro from Tecnológico de Monterrey in Guadalajara. I was wondering about the approximation functions that you made. I think in slide 28, where you presented the function about the estimation of the amplitude that you had to make with the actuators. So the question is, especially for this type of vehicles, how sensitive is this modeling errors that could occur, for example, in this quadratic function that you used to estimate the... Yeah, exactly that one, because there are a lot of cases, no, that depend on the frequency and the pros.
Yeah.
So I think that...
Okay, I understand. Yes, thank you very much. Very nice question. Yes, you are right. It's something which is not easy, first of all, to know. I mean, if you want to get a very nice model, a very precise model, it's possible. It's not impossible, it's possible. I mean, you can use finite element method, and you put a lot of points and you have very precise analysis, no problem. However, since in our case we are interested in control, you have to keep in mind that the model itself should be implemented in real time. And you have real-time constraints, and not any model can be real-time implementable. So this is why we try to look for a compromise. So we try to simplify the model itself. So here we didn't consider that it's flexible. We suppose that it is rigid, okay, and we compute the thrust force like that, okay. We did an experiment with just one fin, So we fix the thing, we put a force sensor, we try to move, we measure the force, the thrust, which is here in blue, okay? And then we try different scenarios with different amplitudes. For each amplitude, you take the mean value of this thrust, okay? We obtain these curves. And for each one of the curves, you have the frequency of oscillation. So finally, we come up with the solution that we decided to keep it at 2 Hertz. So the frequency is fixed. We no longer modify the frequency, and we use the amplitude as a control input. Based on this approximation, so we find this model, we find another model which is written like that, and then since we are looking for what is the amplitude to get a specific thrust, I want 10 thrust 10. What will be the, so we have to inverse this model and we obtain this simplified model. You put here the values of the desired thrust, F and F squared. We replace in this equation and you obtain the amplitude that will gives you. For sure, it's not so precise. However, we rely on the robustness of the control behind to compensate for the errors. We didn't analyze the effect because it's a very good question. What is the effect on the performance, on the tracking, on the precision, and also on the energy? You know, a lot of times when I present this work, they ask me, did you analyze the energy of this compared to classical propeller? If you need more energy, less, normally we need less energy, but we never had the time to work on this problem, on this issue. And the same to your question, yes, it's a simplification. We didn't quantify the effect of this error on the performance of precision, tracking, and so on. However, based on the design of a robust controller, we were able to make a good tracking.
Okay, thank you. It's very interesting.
Yeah, thanks a lot.
Thank you so much, Ahmed, for this lecture. Thank you so much, everyone, for attending this lecture.